Hello there and welcome to Science for Sleep, where curiosity gets cozy, the universe lowers its voice, and even the oldest stars are invited to tell their stories slowly. Tonight, we are drifting toward a small, faint point of light with a very large secret. It is not the brightest star in the sky. It does not blaze like Sirius or sit proudly in a famous pattern like Orion's belt. Most people will never notice it with the naked eye. It is the kind of star that looks, at first glance, like nothing dramatic at all, just another pale spark tucked into the darkness. And yet this quiet star has made astronomers stop, check their numbers, sharpen their measurements, and ask a question that sounds almost impossible. How can something in the universe be so old that it seems to press right up against the beginning of everything? This star is known as HD 140283, but that name, as you may have noticed, is not exactly the sort of name that curls up comfortably beside a pillow. It sounds less like an ancient cosmic survivor and more like the serial number on the back of a toaster. So, over time, it gained a nickname, Methuselah. A name borrowed from the long-lived figure in ancient tradition, a name that immediately suggests age, endurance, and the strange dignity of something that has simply kept going. And that is exactly what makes this star so fascinating. Methuselah is not famous because it is enormous. It is not famous because it is about to explode. It is not famous because it is surrounded by glittering rings, devouring a planet, or firing jets across space like some dramatic cosmic lighthouse. Methuselah is famous because it is old, quietly, stubbornly, almost unbelievably old. Before we go any farther, let me ask you something gentle. Where are you listening from tonight, and what time is it for you right now? Maybe it is late evening where you are, and the day has started to loosen its grip. Maybe it is morning, and you are letting the universe keep you company while the world wakes up. Or maybe you are somewhere in between, in one of those small private hours when the clock says one thing, but your thoughts feel like they're wandering somewhere much farther away. It is a fitting question for a story like this, because tonight we're not just talking about a star, we are talking about time. Not the time that tells you when the kettle has boiled, or when the laundry is done, or when you should probably stop watching one more video and finally sleep. We are talking about time on the scale of galaxies. Time measured in the slow burning of hydrogen, in the formation of heavy elements, in the growth of the Milky Way, in the long quiet stretch between the early universe and the room you're in right now. And if you find this kind of slow cosmic wandering soothing, or if it gives your mind a calm place to rest after a long day, I would be grateful if you gave the video a like and maybe subscribed. It helps this small corner of calm reach other people who may also enjoy drifting through science at a gentler pace. No pressure, of course. The oldest star in our story has been waiting for billions of years, so it probably understands if you need a moment. Now, settle in. Let your shoulders drop a little. Let the ordinary noise of the day begin to move into the background. We're going to follow a beam of starlight that has crossed the quiet space between us and an ancient survivor. Not far by galactic standards, only about a couple of hundred light years away, which in astronomy is almost neighbourly. Not next door, exactly. More like the old house at the far end of the cosmic village, the one with dusty windows and an attic full of memories. But even though Methuselah is nearby in space, it is astonishingly distant in time. It belongs to a very early generation of stars, formed when the universe had not yet made much of the chemical richness that later became planets, oceans, mountains, trees, and people trying to fall asleep while thinking about astronomy. To understand why that matters, it helps to remember that stars are not all born from the same ingredients. The first stars in the universe formed mostly from hydrogen and helium, the simple elements left behind after the Big Bang. They had almost no carbon, oxygen, iron, calcium, or all the familiar heavier elements that make rocky worlds and living bodies possible. Those heavier elements had to be cooked later inside stars, then scattered into space when massive stars died. every later generation of stars was born from material that had been enriched by earlier ones. So when astronomers look at a star and find very little iron, very few heavy elements, they are not just measuring chemistry, they are reading a birth certificate written in starlight. Methuselah has very little iron compared with the Sun. That is one of the clues that tells us it formed very early, before the galaxy had been thoroughly mixed and seasoned by countless generations of stellar deaths. Imagine making soup at the very beginning of a recipe, before the herbs, salt, vegetables, and spices have been added. The first cosmic gas was like that, simple, plain, mostly hydrogen and helium. Later, as stars lived and died, the universe became more complicated. It gained carbon for chemistry, oxygen for water, silicon for rock, iron for planetary cores, and eventually all the strange little ingredients needed for dust, moons, atmospheres, and sleepy humans wondering how old a star can be. Methuselah comes from a time when that cosmic recipe was still nearly bare. That alone would make it interesting. But the real drama came when scientists tried to measure its age. At one point, estimates suggested that Methuselah might be older than the universe itself. Now, that is the kind of sentence that makes even a very calm astronomer sit up a little straighter. A star older than the universe sounds like finding a grandmother who is older than the planet she lives on, or discovering a loaf of bread that somehow predates wheat. It does not mean the universe is broken. It means the measurements are difficult, the uncertainties matter, and nature is very good at reminding us not to get too smug with our calculators. The universe, as far as modern cosmology can tell, is about 13.8 billion years old. Methuselah's age has been estimated at around 14 billion years, with enough uncertainty that it does not truly violate the age of the universe. That uncertainty is important. In everyday life, if someone says a bus arrives at 6 o'clock plus or minus 15 minutes, you probably do not accuse the bus of breaking time if it comes at 5:50. Astronomy is often like that, only the bus is a star, the timetable is billions of years wide, and the passengers are physicists looking worried over coffee. The more carefully scientists measured Methuselah's distance, brightness, temperature and composition, the more the apparent paradox softened. The star was not really older than the universe. It was very, very old, close enough to the beginning that the numbers brushed against the cosmic edge. That is one of the lovely things about this story. It begins with what sounds like a contradiction, but it does not end with a simple trick or a silly mistake. Instead, it opens a doorway into how science actually works. Measurements improve, uncertainties shrink, ideas are tested against new data. A strange result is not thrown away just because it is inconvenient, and it is not blindly accepted just because it is exciting. It is examined, patiently, carefully, sometimes for years. Science, at its best, is not a person shouting, "I have the answer." It is more like a room full of people quietly saying, "Let us check that again." And Methuselah gave them a very good reason to check. The star itself is not young and steady like our sun. It is a subgent, meaning it has begun to leave the long, stable part of its life behind. A star spends most of its lifetime fusing hydrogen in its core, gently balancing the inward pull of gravity with the outward pressure of nuclear energy. Our sun is still in that stage. It is middle-aged, reliable, and occasionally responsible for sunburn. Methuselah, however, has used up much of its core hydrogen and has started to shift into a new phase. It is growing slightly larger and brighter as its internal structure changes. This is useful for astronomers because a star's position in this stage can reveal its age more clearly. In a way, Methuselah is old enough that its body, if we can call a star's layers a body, has begun to show the signs. Of course, a star does not wrinkle. It does not complain about its knees or forget why it walked into a room, although if it did, after more than 13 billion years, we would have to be very understanding. Stars age through physics. Their fuel changes, their cores contract, Their outer layers respond. Their temperature and brightness shift in patterns that can be compared to stellar models. Astronomers build those models using everything they know about nuclear reactions, gravity, opacity, chemical composition, and the behavior of hot plasma. Then they compare the model to the real star. It is not simple. It is not guesswork either. It is more like reconstructing the life of a tree by studying its height, rings, bark, soil, and the weather of a forest that existed before anyone was there to take notes. Methuselah's story also reminds us that the Milky Way itself has a long and complicated past. The star moves quickly through our neighbourhood, and it is associated with the old halo population of our galaxy rather than the younger, flatter disk where the Sun lives. The halo is like the Milky Way's ancient outer memory, a sparse, wide region containing old stars, globular clusters, and leftovers from earlier times. Some halo stars may have formed in small galaxies that later merged into the Milky Way. Others may have formed in the early Milky Way itself, before the galaxy settled into the graceful spiral structure we picture today. Either way, Methuselah is not just an old star. It is a clue to the galaxy's childhood, a small bright fossil from a time before the Milky Way became the familiar river of stars across Earth's night sky. There is something almost comforting about that. We often think of the universe as violent, and of course, it can be. Stars explode, black holes feed, galaxies collide, planets are swallowed, frozen, blasted, or flung into darkness. But Methuselah tells a quieter kind of story. It has survived. While generations of massive stars burned out quickly and died, while galaxies gathered and merged, while the Milky Way built itself piece by piece, this modest star kept shining. Not spectacularly, not loudly, just steadily enough that, much later, on a small rocky planet around a much younger star, a species with telescopes and bedtime routines noticed it and gave it a name. Think about what has happened during Methuselah's life. When it formed, the Sun did not exist. Earth did not exist. The atoms that would later become Earth were still scattered through space or locked inside earlier stars. There were no oceans here, no continents, no moon in our sky, no living cells, no forests, no dinosaurs, no humans staring into the dark wondering what it all means. Methuselah was already ancient before our solar system began to form about 4.6 billion years ago. By the time the first life appeared on Earth, it had already been shining for an almost unimaginable span of time. By the time humans learned to make fire, paint cave walls, build cities, name constellations, and argue about alarm clocks, this star had crossed more cosmic history than our minds can comfortably hold. And yet, when we look at it, we're not seeing it as it is this exact second. We see the light that left it around 2 centuries ago. That is very recent in cosmic terms. If the star were a person sending us a postcard, the message would say, "Still old, still here, hope you're well." The delay is small compared with its lifetime, but it is still a reminder that astronomy is always a form of looking back. Every star in the sky is seen through time. The moon is seen as it was just over a second ago, the sun as it was 8 minutes ago, some galaxies as they were millions or billions of years ago. Methuselah's light does not travel from the dawn of the universe to reach us. It is too nearby for that. But the star itself carries the dawn inside its chemistry. Its light is recent, while its story is ancient. That distinction matters. Sometimes people imagine that looking at old stars means seeing directly back to the Big Bang. Not exactly. A nearby ancient star is more like holding an old coin in your hand. The light from the coin reaches your eyes immediately, but the object itself was made long ago. Methuselah is similar. We are not seeing its birth. We are seeing an old survivor close enough for careful study. That makes it especially valuable. Distant ancient stars are often faint and difficult to measure. Methuselah is close enough, bright enough, and well studied enough that astronomers can examine it in detail. It is not merely a symbol of age, It is a laboratory for cosmic history. There is also a gentle lesson here about uncertainty. People often want science to provide clean, fixed answers. How old is the universe? How old is this star? What happened first? What happens next? And science can answer many of these questions with astonishing precision, but it also carries its uncertainty honestly. Methuselah's age is not just a number, it is a number with error bars. Those error bars are not a weakness, they are a sign of honesty. They tell us how much we know, how much we do not know, and where better measurements may help. In a world where people often speak with far too much certainty about far too many things, there is something refreshing about a star whose story includes the phrase, "within the limits of the data." Maybe that is why Methuselah feels so suited to a quiet night. It does not demand a dramatic conclusion. It invites patience. It asks us to sit with deep time, to accept that some things are too large to grasp all at once, and to let our understanding arrive slowly. You do not have to picture 13 or 14 billion years perfectly. No one really can. You can simply imagine a small old star moving through the galaxy, carrying in its light the memory of a universe that was once simpler, younger, and still beginning to make the ingredients of everything familiar. You can imagine the Milky Way forming around it, the sun arriving much later, Earth cooling, life beginning, and eventually someone like you listening in the dark while the old star continues its quiet work. The first thing to understand about Methuselah is that the sky does not announce it with a grand gesture. There is no bright blue-white blaze catching your eye as soon as you step outside. No obvious jewel hanging low over the rooftops. No familiar pattern that every child learns to point toward. HD 140283 is quiet. It sits in the constellation Libra, not far from the boundary of Ophiuchus, hidden among stars that most casual skywatchers pass over without ever knowing that one of them has been carrying a story from almost the beginning of the universe. If you were outside on a clear night, away from the worst of the city lights, and you looked toward that part of the sky, you would not simply spot it with your eyes. It is too faint for that. You would need binoculars or a small telescope, and even then, it would not look dramatic. It would appear as a modest point of light, a little star among many little stars, not waving, not sparkling in a special colour, not wearing a tiny sign saying, "Excuse me, I may be older than nearly everything you know." That is one of the strangely charming things about astronomy. The most important objects do not always look important. A planet can appear as a small dot. A galaxy can look like a faint smudge. A star that has survived since the earliest ages of the Milky Way can seem like nothing more than a small dry grain of light in a field of darkness. The sky is very good at understatement. It lets the spectacular things hide in plain sight, as if the universe enjoys making us work gently for the good parts. And Methuselah in particular is a perfect example. It is not one of the stars that shaped human mythology for thousands of years. It is not one of the great navigational beacons used by sailors. It is not part of a bold, easy asterism like the Big Dipper or Orion. It is a faint, ancient light in Libra, and for a long time, that is all it seemed to be. Libra itself is a quiet constellation. It represents the scales, and in the night sky it sits between Virgo and Scorpius, two constellations with far more dramatic reputations. Virgo's huge, filled with galaxies beyond easy imagining. Scorpius is bright, curved, and unmistakable, with the red star Antares glowing like a watchful ember. Libra, by comparison, is more restrained. It does not shout, it balances. And perhaps that makes it a surprisingly suitable home, from our point of view, for a star that forced astronomers to balance some of the most delicate measurements in modern astrophysics. Distance against brightness, temperature against age, chemistry against cosmic history, error bars against the age of the universe itself. Libra is the scales, after all, and Methuselah became one of those stars where every small measurement mattered. If you are used to thinking of constellations as fixed pictures, it may help to loosen that idea a little. The stars in Libra are not truly arranged together in space like decorations on a wall. They only look grouped from Earth because we are viewing them from one small location inside the galaxy. Some are close, some are far, some are young, some are old. They are not a family in the usual sense. A constellation is more like a direction on the sky, a familiar patch of the celestial map. It is a way for human beings to make the overwhelming night a little more manageable. We draw borders, we give names. We say this part is Libra, that part is Virgo, over there is Ophiuchus, and somewhere in this quiet region is a star that remembers when the Milky Way was still young. HD 140283 lies about 190 light-years from Earth, which sounds very far until astronomy gently ruins your sense of distance. A light-year is already an enormous measure. The distance light travels in 1 year, moving at about 300,000 kilometers per second. That is fast enough to circle Earth several times in a single second, assuming light had any interest in sightseeing. So 190 light-years is not close in a human sense. You could not visit it. You could not send a postcard and expect a quick reply. Even light itself, the fastest messenger in the universe, takes nearly 2 centuries to make the journey from that star to us. The light entering a telescope tonight left Methuselah when people on Earth were living in a very different world, long before smartphones, long before airplanes, before most of the technologies that now quietly fill our evenings, with glowing rectangles and occasional software updates at the worst possible moment. But in galactic terms, 190 light-years is close. The Milky Way is roughly 100,000 light-years across, so Methuselah is not on the other side of the galaxy. It is in our broader stellar neighbourhood, close enough for astronomers to study in remarkable detail. That closeness is part of why it became so important. Ancient stars can be found in the distant halo of the Milky Way, and in globular clusters, and in the outskirts where old stellar populations drift through space. But distance makes everything harder. A faraway star is fainter. Its light is harder to separate and analyse. Its distance may be more uncertain. Methuselah, however, is near enough that instruments like the Hubble Space Telescope could refine its distance with great care. And once astronomers know how far a star is, they can work out how bright it truly is, not just how bright it appears from Earth. That may sound like a small difference, but with stars it is often the difference between a vague guess and a meaningful biography. Think of it like seeing a candle across a dark field. If you do not know how far away it is, you cannot know whether it is a tiny candle nearby or a bonfire in the distance. A star's apparent brightness is only what reaches your eyes. Its true brightness depends on distance. So when astronomers measure the distance to HD 140283, they are not just plotting a point on a map. They are unlocking the star's real energy output. They are finding where it belongs on the Hertzsprung-Russell diagram, the great chart that compares a star's brightness and temperature. And once they know where it sits on that chart, they can compare it to models of how stars age. The faint point in Libra begins to become a measured object. The little spark becomes a story. Methuselah is not exactly like the Sun. It has a lower mass, and it is very poor in heavy elements compared with the stars around us in the younger disk of the galaxy. Astronomers often use the word metals in a way that would make a chemist blink politely. In everyday life, metals are things like iron, copper, gold, and aluminum. In astronomy, metals means almost everything heavier than hydrogen and helium. Carbon is a metal. Oxygen is a metal. Neon is a metal, even though it would be very difficult to make a saucepan out of it. This is because the universe began mostly with hydrogen and helium, and the heavier elements were built later inside stars. So when a star has very little metal content, it usually means it formed early, before many generations of stars had time to enrich the galaxy. HD 140283 is one of these metal-poor stars. It belongs to an older population, one that carries the chemical fingerprints of the early universe. Its surface does not contain much iron compared with the Sun. That does not mean it has no heavy elements at all. It does have some, and those elements are extremely important because they tell us that Methuselah was not one of the very first stars ever formed. The first stars, often called population 3 stars, are thought to have been made almost entirely of hydrogen and helium. They would have lived fast, burned fiercely, and died before leaving behind the heavier ingredients for later stars. Methuselah came after those first stars had already done at least some of their work. It is ancient, but not first. Old, but not original. A survivor from a time when the universe had begun to make more complicated matter, but had not yet become the richly mixed place we see today. There is a comforting humility in that. Even one of the oldest stars we can study is not the beginning of the story. It is an early page, not the first word. It tells us that before Methuselah, other stars had already lived and died. They had fused simple atoms into heavier ones and scattered them outward. They had changed the chemical future of space. Methuselah formed from gas that had been touched by those earlier deaths. In its faint light is evidence of stars we cannot see anymore. Stars that vanished billions of years before Earth existed. It is a little like finding an old brick in a ruined wall and realizing that the clay in the brick came from an even older riverbed. The object is ancient, but its ingredients carry a deeper past. To the eye, though, none of this is obvious. If you looked at Methuselah through binoculars, you would not see its metal content. You would not see its age. You would not see the delicate ratios of oxygen and iron, or the movement that marks it as a high-velocity star passing through our neighbourhood. You would see a point, a small point. Astronomy often begins with that humbling fact. The universe does not hand over meaning at a glance. It sends light. We build instruments. We split that light into spectra. We measure tiny shifts, tiny absences, tiny lines where atoms have absorbed specific wavelengths. Then, slowly, the point becomes a physical object with temperature, distance, composition, movement, and history. The spectrum of a star is one of the most powerful tools in science, and also one of the most quietly magical, though not magic in the supernatural sense. More like the magic of a receipt that tells you exactly what the universe bought at the atomic shop. When starlight passes through the outer layers of a star, atoms absorb particular colours of light. Each element leaves its own pattern of dark lines, like a barcode written across the rainbow. Hydrogen has its lines, calcium has its lines, iron has many, oxygen leaves clues. By reading those lines, astronomers can determine what a star is made of. They can see whether it is rich in heavy elements like the Sun, or poor in them like HD 140283. They can also measure motion, because if a star is moving toward us or away from us, its light shifts slightly toward blue or red. The star's light becomes not just illumination, but information. Methuselah has been known as a high-velocity star for a long time. That means it moves through the galaxy faster and differently than many stars in the Sun's local neighbourhood. This is another hint that it does not belong to the ordinary younger disk population around us. The Sun moves with the general rotation of the Milky Way's disk, along with many stars formed from the more enriched gas of later times. Methuselah seems more like an old traveller cutting through the neighbourhood on a different path, perhaps associated with the halo, that sparse ancient component surrounding the galaxy. The halo is not a bright ring you can see in the sky. It is a huge, diffuse population of old stars and clusters spread around the Milky Way like the memory of earlier mergers and early formation. If the galactic disk is the busy town centre, the halo is the old countryside beyond it, quiet, wide, and full of things that have been there longer than the town itself. That gives Methuselah a particular kind of dignity. It is not simply sitting in Libra like a decorative light. It is moving. It has a path. It has spent billions of years orbiting through the gravitational field of the Milky Way, passing through regions that have changed again and again. It has seen, in the broad physical sense, the galaxy grow around it. Of course, stars do not see. They do not watch history the way we do. They have no memory in a human sense. But their motions and chemistry preserve evidence. They carry records without knowing they carry them. That may be why ancient stars feel so moving to us. They are not alive, yet they are witnesses. They do not speak, yet we can read them. They do not remember, yet their light has kept the receipts. The name Libra means scales, and there is another way that feels appropriate. When astronomers study Methuselah, they are always weighing one thing against another. The star appears faint because it is not a blazing giant, and because it is far beyond ordinary human distance, but it is close enough to measure. It looks unremarkable, yet it carries extraordinary age. Its light reaching us is only 190 years old, but the star producing that light is more than 12 or 13 billion years old, depending on the exact measurement and model being considered. It is nearby and ancient at the same time. That combination is what makes it so valuable. A distant galaxy can show us the universe as it was long ago, because its light took billions of years to arrive. Methuselah does something different. It lets us study an ancient object almost in our backyard. Not an ancient image from across the cosmos, but an ancient survivor close enough for detailed inspection. There is an important difference there, and it is worth lingering over. When a telescope looks at a galaxy 13 billion light-years away, it sees that galaxy as it was 13 billion years ago. The light itself is ancient. With Methuselah, the light is not that old. It has only travelled for about 190 years, but the object is ancient. The star has been shining for nearly the whole age of the universe. That makes it more like meeting a very old person in your own town rather than reading a letter from someone young in a distant past. The person is here now, but their life stretches back through history. Methuselah is here, astronomically speaking, in our neighbourhood. Its light is recent, its body is old, its chemistry is old, its place in stellar evolution is old. It is the difference between looking back through a telescope and looking at a fossil under a lamp. And the fossil image is useful, though we should be careful with it. A fossil on Earth is usually the remains of something dead. Methuselah is not dead. It is still shining. It is still producing light. It has moved beyond the most stable, long-lasting part of its life, becoming a subgiant, but it has not ended. That makes it more like a living fossil if we borrow the phrase gently. Not a frozen remnant, but a working star whose very existence carries old information. Its low metal content is a sign of the universe it came from. Its age tells us about early star formation. Its motion tells us about the old galactic population it belongs to. Its faintness on the sky is only the surface of the story. There is also something quietly funny about the fact that a star can be famous among astronomers and almost invisible to everyone else. Human fame usually comes with attention, lights, noise, a name repeated often enough that it becomes impossible to ignore. Stellar fame is different. A star can be one of the most important objects in astrophysics and still require a finder chart. It can challenge models of cosmic age and still be ignored by a person walking the dog under a clear sky. The universe does not care much for publicity. It simply places its clues where they are and lets curiosity do the rest. If you were trying to find Methuselah from Earth, you would first need to know when Libra is visible from your location. You would need a dark enough sky, or at least optical help. You would need to move from brighter guide stars to fainter ones, stepping carefully through the star field. There is a patience to that process that fits the object itself. You cannot rush toward this star. You cannot simply glance upward and be done. You have to slow down, check the chart, adjust the view, let your eyes settle, and then, there it is. Not as a dramatic revelation, but as a small confirmation. A point of light where the map said it should be. A quiet yes from the sky. That kind of observation may not sound spectacular, but it has a special pleasure. There is a difference between being dazzled and being connected. A bright meteor dazzles. A total eclipse dazzles. Saturn through a telescope absolutely dazzles, especially the first time, when your brain politely refuses to believe that the tiny ring thing is real, and not a sticker someone placed inside the eyepiece. Methuselah does not dazzle in that way. It connects. It connects the observer to a chain of thought stretching from backyard astronomy to space telescopes, from simple starlight to the age of the universe, from a faint dot in Libra to the first generations of stars. And maybe that is why this part of the story matters so much. Before we talk about the nickname, before we examine the age problem, before we follow the measurements that made scientists wonder whether the star was older than the universe, we need to sit with its plain appearance. Because the plainness is part of the wonder. HD140283 reminds us that deep time is not always hidden behind dramatic scenery. Sometimes it is stored in a pale, ordinary-looking point. Sometimes the oldest things do not look old. They do not glow red and weary. They do not lean on cosmic walking sticks. They simply keep shining, while younger and brighter objects grab the attention. The sun, our own familiar star, is much younger than Methuselah. It formed about 4.6 billion years ago from gas already enriched by many previous generations of stars. Compared with HD 140283, the Sun is a latecomer. Not young in the way a mayfly is young, but young in the long arithmetic of the galaxy. By the time the Sun began to shine, Methuselah had already endured for billions upon billions of years. It had already travelled through the Milky Way's changing structure. It had already survived events that shaped the galaxy before our solar system had any dust to call its own. The atoms that would become Earth were not yet gathered into a planet. The future oceans, rocks, trees, animals and listeners were still scattered possibilities, and Methuselah was already there, burning gently. That comparison can make our daily clocks feel both tiny and precious. We count minutes. We notice deadlines. We worry when a message is not answered quickly. We measure sleep in hours and work in schedules and weekends in sadly small portions. Meanwhile, a faint star in Libra measures its life in billions of years. Neither scale cancels the other. Your minutes matter because you live inside them. The star's billions matter because they show us the larger story those minutes belong to. Astronomy does not make human life meaningless. It gives it context. It says here is the vastness around you, and somehow, within that vastness, you are awake for a moment, able to notice. Finding HD 140283 was not like discovering a comet with a bright tail or spotting a new planet wandering against the stars. There was no sudden flare in the night, no urgent telegram sent between observatories, no astronomer running into the street in slippers to announce that the universe had just revealed one of its oldest survivors. The story was slower than that, and in a way, more fitting. This star entered human knowledge the way many quiet things do, by being recorded, measured, compared, and then noticed again with better tools. At first it was simply a star with a position, a faint point in the constellation Libra, too dim for ordinary naked eye fame. Then it became a catalogue entry. Then it became an unusual moving star. Then it became a chemically strange star. Then, after decades of patient work, it became something far more dramatic than it looked, a nearby relic from the early universe. That is a good thing to remember when we talk about astronomy. Discovery is not always a single moment. Sometimes discovery is a staircase. One observer places the first step by recording where a star is. Another places the next by measuring how it moves. Someone else takes its spectrum and notices that its light is missing the usual chemical richness. Later, a telescope in orbit measures its distance with better precision, and suddenly the whole structure becomes clear. The star was not hiding because it was secretive. It was hiding because its importance was written in details too fine for early instruments to read. It was there all along, calmly shining,
while generations of astronomers built the tools needed to understand what kind of object they were looking at. The name HD 140283 tells us where one of those early steps came from. The HD stands for the Henry Draper Catalogue, one of the great star cataloguing efforts of the early 20th century. Henry Draper was an American physician, an amateur astronomer, who helped pioneer stellar photography and spectroscopy, and after his death, his name became attached to a huge project at Harvard College Observatory. Astronomers and skilled classifiers examined photographic plates and sorted stars according to the patterns in their spectra. These were not glamorous-looking objects in the way we might imagine astronomy now. They were glass plates, dark rooms, tiny marks, careful eyes, and a lot of patient work. If the universe has a filing cabinet, this was one of the drawers being built. A catalogue number like HD 140283 may sound cold, but there is something quietly impressive about it. It means the star had been brought into a human system of order. It had been placed among hundreds of thousands of other stars, each with a label, each with a spectrum, each waiting for someone to ask a better question. We often prefer names that sound warm or legendary, and understandably so. Methuselah is easier to remember than HD 140283, but the catalogue name has its own dignity. It belongs to the long tradition of humans trying to make the sky searchable. Before you can understand a star, you usually have to find it in the great crowd. Before you can notice that one member of the crowd is extraordinary, you need to know where everyone is standing. At first, HD 140283 was interesting, not because anyone knew it was ancient, but because it moved strangely fast across the sky, not fast like a meteor, of course. Stars are so far away that even when they are travelling through space at enormous speeds, they appear to creep across the background over years and decades. But with careful measurements, that creep can be detected. Astronomers call this proper motion. It is the apparent motion of a star across the sky, measured against more distant background objects. Most stars shift only slightly from year to year. HD 140283 had enough proper motion to stand out. It was not fixed in place. It was crossing our celestial view with the urgency of an old traveller who had no intention of staying neatly with the local crowd. That movement mattered. A star's motion can tell us something about where it belongs in the galaxy. The Sun and many nearby stars move together around the Milky Way in the broad rotating disk, like leaves carried by the same slow current. But some older stars move on more tilted, stretched, or unusual paths. They may belong to the halo, the ancient sparse population surrounding the galaxy. These stars often have high velocities relative to the Sun. They are not necessarily racing because they are energetic in some dramatic personal sense. They are following old orbits shaped by the early history of the Milky Way, by gravitational encounters, by the assembly of the galaxy itself. Their motion is a clue to ancestry. HD 140283 also shows a slight blue shift, meaning its light is shifted towards shorter wavelengths because it is moving toward us along our line of sight. That detail combines with its sideways motion to reveal a star travelling through our region of the galaxy in a way that does not match the ordinary younger disk population. If you imagine the nearby stars as people walking calmly in the same direction along a wide street, Methuselah is the elderly stranger cutting diagonally across the road with surprising speed, wearing an old coat and carrying papers no one else can read. You might not stop at first, but if you notice the movement, you begin to wonder where that traveller came from. In the early 20th century, spectroscopy was becoming one of the most powerful ways to understand stars. It had already changed astronomy from a science of positions and brightness into a science of physical identity. Before spectroscopy, stars were mostly lights on a map. After spectroscopy, they became hot spheres with temperatures, compositions, motions, and life stages. A spectrum lets astronomers split starlight into its colours and examine the dark absorption lines left by atoms in the star's atmosphere. Each element makes its own pattern. Hydrogen leaves certain lines, calcium leaves others. Iron, being a generous overachiever in the world of spectral lines, leaves many. The star's rainbow becomes a chemical message. HD 140283 began to look truly unusual when its spectrum showed that it was poor in heavy elements. In the 1950s, Joseph Chamberlain and Lawrence Aller studied stars including HD 140283 and found that its chemical composition was very different from the Sun's. It had far less iron and calcium. At the time, that was not merely a small detail. It was a clue that the star belonged to an older population. The universe did not begin with much iron or calcium. Those elements had to be made in stars and spread through space by stellar death. A star with very little of them is like an old document written before the language had gained many of its later words. This is where the story starts to deepen. A fast-moving star is interesting. A nearby star is useful. A metal-poor star is historically important. But a nearby, high-velocity, metal-poor star that is also bright enough for detailed study becomes a treasure. Not a treasure in the pirate sense, although astronomers would probably enjoy a chest full of observing time more than gold coins. It is a scientific treasure because it gives us a close look at material from the young galaxy. Many of the most ancient stars are faint, distant, or tucked inside globular clusters where crowding and distance make precise measurements difficult. HD 140283, by comparison, sits close enough to be examined with unusual care. It is like finding an ancient manuscript not locked in a faraway archive, but sitting on a shelf in the neighbourhood library. For many years, HD 140283 was known among specialists as an old, metal-poor, high-velocity star. That may not sound like the sort of description that makes headlines, but in astronomy, it is enough to raise eyebrows. The star belonged to a class often called Population 2, meaning old stars formed from gas that had not yet been enriched with many heavy elements. Population 1 stars, like the Sun, are younger and more metal-rich. The naming is slightly confusing because Population 1 came before Population 2 in historical classification, even though Population 2 stars are older. Astronomy does this sort of thing sometimes. It is a science of sublime order interrupted by occasional naming decisions that feel as if someone filed the drawers during a thunderstorm. The important point is that Population 2 stars help us look back toward the Milky Way's early life. They are not first-generation stars because they do contain some heavy elements, but they are close enough to the beginning to preserve traces of the universe shortly after the first stars had lived and died. The first stars, the hypothetical Population 3 stars, would have formed from nearly pure hydrogen and helium. They were probably massive, short-lived and brilliant, and they are gone now. We do not have one sitting nearby for easy inspection. That would be convenient, but the universe rarely arranges itself for our convenience. Instead, we study stars like Methuselah, which formed after the first enrichment had begun but before the galaxy became chemically mature. It took another kind of measurement to turn HD 140283 from an old star into a cosmic celebrity. Astronomers needed to know its distance precisely. Distance is one of the great headaches of astronomy. A star's apparent brightness means very little until you know how far away it is. A dim-looking star may be nearby and modest, or far away and very powerful. Without distance, you cannot know its true luminosity. Without true luminosity, you cannot place it accurately on the stellar life chart. Without that placement, estimating its age becomes much less certain. So distance is not just geography. Distance is biography. For nearby stars, one of the best methods is parallax. Hold out a finger in front of your face, close one eye, then switch eyes. Your finger seems to jump against the background. That little jump happens because your two eyes view it from slightly different positions. Astronomers do something similar with Earth's orbit. They observe a nearby star from one side of Earth's orbit around the Sun, then again 6 months later from the other side. The star appears to shift slightly against the more distant background. The shift is tiny, but it reveals distance. For HD 140283, better parallax measurements were essential. The Hubble Space Telescope helped refine that distance by using its fine guidance sensors, instruments that can measure extremely small changes in position. Hubble is famous for beautiful images, glowing nebulae, colliding galaxies, and those deep-field views where nearly every speck is another galaxy. But some of its most important work is less showy. It can measure positions with remarkable precision. It can do the careful, needle-threading work of astrometry. For Methuselah, that mattered enormously. Once Hubble narrowed the uncertainty in the star's distance, astronomers could better determine its true brightness, compare it with stellar evolution models, and sharpen the estimate of its age. That was when the story moved from specialist interest to public fascination. The refined age estimate came out to around 14.5 billion years, with an uncertainty of about 800 million years. The universe itself is about 13.8 billion years old. At first glance, this sounded like a problem. A star older than the universe is not a small scheduling error. It is the kind of thing that makes people imagine cosmologists staring at a chalkboard and quietly asking whether anyone still has the receipt for the Big Bang. But the uncertainty is crucial. With the error range included, the star's age does not truly contradict the age of the universe. It means the star is extremely old, close to the cosmic beginning, and difficult to measure with perfect certainty. Still, the phrase was irresistible. A star that seemed older than the universe. That was when the nickname Methuselah took hold in popular writing. In biblical tradition, Methuselah is famous for extreme longevity, living 969 years. Whether one approaches that as religion, literature, cultural memory, or simply a familiar old name, the association is clear. Methuselah means old, very old. Old enough that ordinary age comparisons begin to feel inadequate. So HD 140283, with its catalogue number and its impossible-sounding age estimate, became the Methuselah star. It was a nickname made for headlines, but also one that captured something true. This star is not merely old in a technical sense, it is old in a way that forces the imagination to stretch. There is a small danger in nicknames, though. They can simplify a story too much. Methuselah sounds like the oldest star, full stop, as if the case is closed and a golden medal has been placed on its glowing surface. In reality, astronomy is more careful. HD 140283 is one of the oldest well-studied stars in our neighbourhood, and for a time it was widely described as the oldest known star with a well-determined age. Other ancient stars exist. Some stars in globular clusters are also extremely old. Some very metal-poor stars may be older or comparable, and newer methods can revise estimates. The title is not a permanent crown nailed to the sky. It is a sign of how important this star has been as a test case. Methuselah is famous not only because of the number attached to its age, but because we can study it so well. The nickname also says something about us. We do not live easily with catalogue numbers. We need stories. We need a way to carry large ideas in smaller words. HD 140283 is precise, but it does not make the mind lean closer. Methuselah does. The name turns a star into a character. It does not change the science, of course. The star does not know what we call it. It continues fusing and expanding and moving through the galaxy with complete indifference to human naming habits. But for us, the name helps. It gives the old point of light a human handle. It lets people who are not specialists remember that there is a nearby star so ancient that it once seemed to challenge the universe's own age. In a bedtime sort of way, there is something pleasing about how the name and the science meet. The science is careful. Parallax, spectroscopy, luminosity, metallicity, stellar models, uncertainties. The name is simple, Methuselah. One side belongs to equations and telescopes, the other belongs to storytelling, and astronomy has always needed both. We measure because we want to know what is true. We name because we want to feel our way into the truth without losing our human sense of wonder. A sky filled only with numbers would be accurate but chilly. A sky filled only with myths would be beautiful but untested. Methuselah gives us both, a precise object with a warm old nickname, a star that can sit comfortably in a scientific paper and in a sleepy story. The discovery, then, was not a single event, but a long unfolding. The star was catalogued, its motion was noticed, its spectrum was studied, its lack of heavy elements revealed its ancient nature, its distance was refined, its age was compared with the age of the universe. And at the end of that chain, a faint star in Libra became one of the most famous old stars in modern astronomy. That slow process matters because it shows how the universe often reveals itself, not with one dramatic answer, but with evidence accumulating like snow on a quiet roof. A measurement here, a spectrum there, a better telescope later, and eventually the shape of the story appears. It is worth pausing with the people behind those steps too, even if only gently. The early cataloguers who sorted stars by spectra were doing work that could feel repetitive, but it laid the foundation for nearly everything that followed. The Mount Wilson observers who measured spectra and motions helped turn faint points into physical systems. The mid-century astronomers studying metal-poor stars helped connect chemistry with galactic history. The Hubble team refined the parallax and gave the age estimate the precision that brought Methuselah to wider attention. None of these people working in their own moment had the whole story from the start. Each held a piece. That is often how science works. It is not only flashes of genius, it is also careful continuity. And perhaps that is why HD 140283 is such a satisfying star to follow. Its history of discovery mirrors its own nature. It is patient. The star has lasted for almost the entire life of the universe, and our understanding of it also required patience. Quick glances didn't reveal it. Simple brightness did not reveal it. The first catalogue entry did not reveal it, but repeated attention did. There is a small lesson there, not too heavy, just enough to carry quietly. Some things become extraordinary only when you keep looking, so when we call it Methuselah, we are not just giving a nickname to an old star. We are acknowledging a chain of careful noticing that turned an obscure catalogue number into a cosmic witness. HD140283 was found by being measured more than once, by being taken seriously when it looked odd, by being revisited when better instruments became available. Its name became famous because its age brushed against the deepest timeline we have, the age of the universe itself. And now that we know why this faint star earned such a legendary name, the next question becomes even more interesting. How do astronomers actually measure the age of a star that has no birth certificate, no rings like a tree, and no memory of the morning it first began to shine? A star does not carry a little certificate from the cosmic hospital saying when it was born, which is frankly inconsiderate of it. There is no tag tied around it with a date, no ancient record book floating nearby, no first photograph of a newborn star swaddled in dust and hydrogen. When astronomers look at HD 140283, they are looking at a star that has been shining for almost the entire history of the universe. But the star itself does not tell the story plainly. It does not say, "I formed on this exact morning shortly after the first great generation of stars began changing the chemistry of space." It simply shines. So astronomers have to do what they often do best. They gather clues from light, distance, motion, chemistry, temperature, brightness, and physics, then assemble those clues into the most careful estimate possible. Measuring the age of a star is not like checking a calendar. It is more like trying to determine the age of an old house by studying the wood, the foundations, the dust in the attic, the style of the nails, and whether the roof has started to sag. For some stars, the task is easier than for others, although easy is a generous word in astrophysics, a field where even the simple things are usually several equations deep and slightly warm. If a star is in a cluster, astronomers have a useful advantage. Stars in a cluster usually form together from the same great cloud of gas. That means they are roughly the same age, even though they may have different masses. Some are small and cool, some are large and bright, some burn through their fuel quickly, some take their time as if they know the universe rewards patience. By plotting the stars in a cluster on a chart of brightness and temperature, astronomers can see which stars have already left the main sequence, the long stable part of a star's life when it fuses hydrogen in its core. The point where stars begin to peel away from that stable line is called the turn-off, and it is one of the best age markers we have. A young cluster still has big, hot, bright stars on the main sequence. An old cluster has lost those short-lived stars because they have already evolved onward or died. The more massive stars burn fast, like people who use all their holiday energy on the first morning and then need a nap. Smaller stars burn slowly and can last for many billions of years. That method works beautifully for groups of stars, especially globular clusters, those ancient spherical gatherings that orbit the Milky Way like old lanterns around a city. But HD 140283 is not sitting in a neat cluster where all its siblings are lined up for comparison. It is a field star, an individual traveller moving through our neighbourhood of the galaxy. That makes its age harder to measure. Without a cluster around it, astronomers cannot simply compare it to a whole family of stars born at the same time. They have to understand the star itself. They need to know how luminous it really is, how hot its surface is, what it is made of, how much mass it has, and what stage of life it has reached. Then they compare all of that to models of stellar evolution, which are basically long, careful calculations of how stars with different masses and compositions should change over time. The first major clue is brightness, but not the kind of brightness your eyes would notice from Earth. Apparent brightness is how bright a star looks to us. True brightness, or luminosity, is how much energy the star is actually producing. Those are not the same thing. A candle close to your face may look brighter than a street lamp far down the road, but that does not mean the candle is more powerful. So before astronomers can judge a star's real brightness, they must know its distance. This is why the distance to Methuselah mattered so much. If you know how far away a star is, you can convert its apparent brightness into true luminosity. Without that distance, the star's age estimate becomes much less secure. For nearby stars, one of the most elegant ways to measure distance is parallax. It is a simple idea carried out with extraordinary precision. Hold up your finger in front of your face and look at it with one eye closed, then switch eyes. Your finger appears to jump against the background, not because your finger has actually leapt sideways, though that would make breakfast more surprising, but because you are viewing it from two different positions. Astronomers do something similar using Earth's orbit around the Sun. They observe a nearby star, then observe it again months later when Earth is on the other side of its orbit. The star seems to shift slightly against more distant background stars. That tiny shift reveals its distance. The smaller the shift, the farther away the star. With HD 140283, Hubble's fine guidance sensors helped measure this tiny shift with great precision. That may sound less glamorous than taking a dramatic image of a nebula, but it was crucial. A better parallax meant a better distance. A better distance meant a better luminosity. A better luminosity meant a better placement on the star's life chart, and that, in turn, meant a better age. Sometimes the universe gives us a mystery, and the key is not a louder telescope or a more colourful picture, but a more careful ruler. Hubble narrowed the distance to about 190 light-years, which placed Methuselah close enough for detailed study but far enough away to remind us that even our stellar neighbours live at distances that make human travel plans look very silly. Once luminosity is known, astronomers also need the star's temperature. Temperature can be estimated from the colour of the star and from its spectrum. Hotter stars shine more blue-white, cooler stars shine more red-orange. But with an object like Methuselah, astronomers are not simply glancing at a colour and guessing. They examine the star's spectrum, the spread of its light into different wavelengths, and look at the pattern of absorption lines carved into that light by atoms in the star's atmosphere. Those lines reveal both temperature and composition. They are like the star's fingerprints, except instead of being left on a glass, they are printed across a rainbow. The composition is especially important for ancient stars. HD140283 is metal poor, meaning it contains very little of the heavier elements compared with the Sun. In astronomy, remember, metal means almost everything heavier than hydrogen and helium, which still feels like astronomy is playing a small prank on chemistry. Iron, oxygen, carbon, calcium, magnesium, silicon, all of these count as metals in this context. The early universe was mostly hydrogen and helium. Heavy elements were made later inside stars and spread into space by supernovae and stellar winds. So a star with very little iron is usually a star that formed before the galaxy had become heavily enriched. Methuselah's low metal content is one of the strongest signs that it belongs to an early population. But metal-poor chemistry does not by itself give an exact age. It tells astronomers that the star is old, but not precisely how old. It is like seeing an antique chair and knowing it is not from last week, but still needing expert work to decide whether it is 80 years old, 200 years old, or something that should not be sat on without permission. To refine the age, astronomers compare the star to theoretical models known as isochrones. An isochrone is a curve on a chart showing where stars of a certain age and chemical composition should appear, depending on their masses and life stages. Place a real star on the chart using its temperature and luminosity, add its composition, and you can see which model age fits best. For a star like the Sun, which is still comfortably on the main sequence, this can be difficult. A middle-aged main sequence star may change slowly, so its brightness and temperature do not reveal its age sharply. It is a bit like trying to guess the age of an adult by watching them sit quietly in a chair. You might get a broad range, but not a precise number. Subgents are more helpful. A subgent has begun leaving the main sequence because the hydrogen in its core is running low. Its structure is changing more noticeably. It grows brighter, its outer layers begin to respond, and its position on the Hertzsprung-Russell diagram becomes more sensitive to age. HD140283 is a subgiant, which makes it a particularly valuable ancient star. It has reached the stage where its age is written more clearly in its current state. That does not mean the answer becomes simple. Stellar models must include many pieces of physics. They must account for nuclear reaction rates, the way energy travels through the star, the pressure and temperature of the interior, the star's chemical mix, the amount of helium, and subtle processes such as diffusion, where heavier elements can slowly settle or shift inside the star over time. Oxygen is especially important for HD140283's age estimate. The amount of oxygen in the star changes how the models behave, because oxygen affects the opacity and internal structure, and that affects how quickly the star evolves. A small change in the assumed oxygen abundance can shift the estimated age by a meaningful amount. So when astronomers say Methuselah is about this old, plus or minus that much, they are not shrugging. They are being honest about all the small ingredients that feed into the result. There is a very human lesson tucked inside those error bars. People sometimes hear uncertainty and think it means scientists do not know what they're doing. But uncertainty is not ignorance. It is measured caution. It is the difference between saying, "I have no idea where I park the car," and saying, "I parked it somewhere on this street between the bakery and the tree, but probably closer to the tree." One is confusion. The other is a range. In astronomy, a range is often a triumph. When the object is 190 light-years away, and more than 12 billion years old, being able to narrow its age to within hundreds of millions of years is not failure. It is astonishing. It is the cosmic equivalent of estimating the age of an ancient candle from another town by analysing the warmth of its flame through a keyhole. With Methuselah, the result became famous because the age estimate came out so close to the age of the universe. Around 14.5 billion years, plus or minus 800 million years, sounds awkward when the universe itself is about 13.8 billion years old. This is where many people first hear about the star and imagine a paradox. But the uncertainty range matters. If the estimate has a margin of error, then the star can still be younger than the universe while being extremely old. It is not a genuine contradiction, more a warning light on the dashboard that says, "Please check the assumptions carefully." And astronomers did. They looked again at the distance, the temperature, the oxygen abundance, the physics in the models, and the details of the measurement. The star did not overthrow cosmology, it sharpened the conversation. That sharpening is valuable. Very old stars are independent checks on the history of the universe. Cosmologists estimate the age of the universe from measurements such as the cosmic microwave background, the expansion rate, and the overall model of cosmic evolution. Stellar astronomers estimate the ages of the oldest stars using completely different tools. If the oldest stars all came out much older than the universe, that would be a serious problem. If they come out slightly younger, or close within uncertainty, that gives confidence that the broader picture is consistent. Methuselah sits right near that boundary, which makes it exciting. It is like a very old witness whose testimony must be handled carefully, because it concerns the first few minutes of a very long case. Another method of stellar dating useful in other stars is astroseismology. This is the study of tiny vibrations inside stars. Stars can ring like bells, although very large, very hot bells that should not be placed near children or curtains. The frequencies of those vibrations reveal internal structure, including density and age-related changes. Space missions have used this technique for many stars, especially solar-like stars and red giants. It is a beautiful idea, listening to a star's interior through the small changes in its light. For Methuselah, the classic age story is mainly built from parallax, luminosity, temperature, chemistry, and stellar modelling, but the broader field of stellar ages increasingly combines different methods. Each method gives another way to test the others, and when several independent clues point in the same direction, confidence grows. There are also rotation and magnetic activity methods for younger stars. Young stars often spin faster and show stronger magnetic activity. Over time, stars like the Sun lose angular momentum through stellar winds and slow down. Astronomers can sometimes use rotation rate as an age clue, a technique called gyrochronology. But this is not very useful for a star as ancient and evolved as HD 140283. By the time a star is that old, especially when it has left the main sequence, the simple rotation clock is no longer the right tool. It is like trying to use a school timetable to understand the retirement plans of a mountain. Different stages of life require different clocks. Mass is another key part of the puzzle. Massive stars live short lives because they burn through fuel quickly. Low-mass stars live much longer. HD 140283 has less mass than the Sun, which helps explain how it could survive for so long. A massive early star would have died quickly, perhaps after only millions of years. Methuselah endured because it was modest. That is a nice reversal of what we often expect. The brightest and most massive stars dominate photographs, but they are temporary fireworks. Smaller, quieter stars can last across enormous spans of time. In stellar life, being dramatic is often bad for longevity. The universe has a way of rewarding restraint. To measure a star's age, then, astronomers are really measuring its whole situation. They ask, how far away is it? How bright is it truly? How hot is its surface? What elements are present in its atmosphere? How much iron does it have compared with hydrogen? How much oxygen? What phase of life is it in? What mass best matches its observed properties? Which stellar model fits all of this without contradicting known physics? And how large are the uncertainties from each measurement? The final age is not a number pulled from one observation. It is the meeting point of many lines of evidence. If you picture this gently, you might imagine astronomers placing Methuselah on a great cosmic map. Not a map of space only, but a map of life stages. The main sequence is a long road. The subgiant branch is a turning path. The red giant phase waits farther along. Methuselah's position on that map tells us it has spent a very long time burning hydrogen and has now begun the slow transition away from that stable life. Its chemistry tells us it was born early. Its distance tells us how luminous it really is. The models tell us how long a star of that composition and mass would take to reach this point. When all the pieces are placed together, the old star begins to reveal its age, not by speaking, but by fitting. There is something deeply patient about the whole process. A star spends billions of years becoming what it is, and astronomers spend decades improving the measurements that let us understand it. Hubble's parallax did not make Methuselah old. The star was old long before humans existed, long before Earth existed, long before the sun gathered itself from gas and dust. What Hubble did was help us see the age more clearly. It tightened the ruler. It reduced one source of uncertainty. It turned a very old star into a sharper test of stellar physics and cosmology. And this is where the story becomes especially interesting for our quiet journey. Because once astronomers measured Methuselah carefully, they found themselves standing before a number that seemed almost too large. Not because the star looked ancient in a telescope, it did not. Not because it was surrounded by ruins, it was not. But because the physics, the distance, the brightness, the temperature, the low metal content and the subgent stage all pointed toward a star born extremely early. So early that for a while, the simplest version of the number appeared to push beyond the age of the universe itself. And that is the kind of puzzle that does not make science collapse, but does make it lean forward, adjust its glasses and ask very quietly, what exactly are we missing? The mystery begins with a sentence that sounds as if it should not be allowed to exist. There is a star near our part of the Milky Way that once seemed older than the universe. Not older than Earth, which would be easy enough. Not older than the Sun, which many stars are. Not older than the Milky Way's familiar spiral shape, which has changed over time anyway. Older than the universe itself. And that is the kind of claim that makes the mind pause, the way it might pause if someone told you they had found a photograph of their grandparents taken before cameras were invented. Something, somewhere, has to be examined more carefully. Either the photograph is not what it seems, the date is wrong, the invention happened earlier than expected, or someone has been very creative with the family album. With HD 140283, the situation was not quite as absurd as it sounded in headlines, but it was still serious enough to be fascinating. Stars must be younger than the universe. That is not a small preference, it is a basic requirement. The universe is the setting in which stars form. It provides the space, the matter, the laws of physics, and the early hydrogen and helium from which the first stars were born. A star cannot form before there is a universe to contain it, just as a biscuit cannot be older than the oven, the kitchen, and the person who forgot to set a timer. So when astronomers measured Methuselah and found numbers that appeared to press beyond the universe's age, the result did not mean anyone had discovered a star from before time. It meant that some part of the measurement, the model, or the uncertainty needed to be understood with great care. The age of the universe itself is not guessed casually. It comes from several lines of evidence, including the expansion of space and the cosmic microwave background, the faint afterglow left from the early hot universe. Modern cosmology places the universe at about 13.8 billion years old. That number is not simply printed on a cosmic birthday card, although that would be helpful. It is inferred from measurements of how the universe expands, what it contains, and how early light was stretched and cooled as space grew. The result is one of the great achievements of modern science. A universe with a measured age, not merely an ancient forever, but a history with a beginning we can model. Then there was Methuselah. Early age estimates for HD 140283 were uncomfortably high, at one point around 16 billion years. Now 16 billion years is a wonderful age for a star if your universe is older than that. But if your universe is 13.8 billion years old, it becomes a problem. It is like inviting someone to a birthday party and having them arrive carrying a cake that says they are older than the host. You do not throw the person out immediately, you check the cake, you check the candles, you check whether someone used the wrong icing number. In science, this checking is not an embarrassment, it is the work. The first thing to understand is that age estimates are not single perfect numbers. When scientists say a star may be 14.5 billion years old, they do not mean they watched it being born and counted every year since, perhaps with a very large notebook and excellent patience. They mean that the star's observed properties best match stellar models of a certain age. But every observed property has some uncertainty. Distance has uncertainty. Brightness has uncertainty. Temperature has uncertainty. Chemical composition has uncertainty. The physics in the models, though extremely well tested, still includes assumptions and approximations. These do not make the result useless, they make it honest. That little phrase, plus or minus, does a tremendous amount of work. A star estimated at 14.5 billion years old, plus or minus 800 million years, might actually be closer to 13.7 billion years old within the measurement range. And suddenly, the star is no longer older than the universe. It is just extremely old, nearly as old as it can be without breaking anything. Error bars are not decorations attached to a result after the exciting part. They are part of the result. They are the scientific equivalent of saying, here is what we think, and here is how precisely we think we know it. Without them, numbers can become misleadingly confident, which is one of the easiest ways for a perfectly respectable star to become a cosmic troublemaker. In Methuselah's case, one of the most important improvements came from measuring its distance more precisely. If you do not know exactly how far away a star is, you cannot know exactly how luminous it truly is, and if you do not know how luminous it truly is, you cannot place it precisely on the map of stellar evolution. Hubble's fine guidance sensors helped measure the star's parallax with much better precision than earlier measurements. That sharpened the distance. The sharper distance sharpened the luminosity. The sharper luminosity let astronomers compare the star more accurately to evolutionary tracks and isochrones, those theoretical curves that show where a star of a given composition and age should be. But even after the distance improved, the age still came out very high. That is where the story becomes more subtle. At first, one might imagine that the only problem had been distance, and once that was fixed, the mystery would quietly go away, perhaps embarrassed by all the attention. But the age of HD 140283 depends strongly on other ingredients too, especially its chemical composition. For a very metal-poor subgiant like Methuselah, oxygen is particularly important. The amount of oxygen in the star affects the models used to determine how quickly it evolves. Change the oxygen abundance slightly, and the inferred age can shift by hundreds of millions of years. That may sound enormous, but on a 13 billion year timescale, it is the difference between an elderly star politely standing inside the universe's age and one awkwardly placing a foot over the line. This is why the older than the universe mystery is not just a story about one star. It is a story about the difficulty of measuring deep time. The universe does not make ancient objects easy to date. A star's surface chemistry may have changed slightly over time because elements can settle or diffuse within it. Its exact temperature may be measured with a range. Its oxygen lines in the spectrum may be weak or affected by details of stellar atmosphere physics. Different models may handle mixing, diffusion, convection, and nuclear reaction rates in slightly different ways. Each small issue is manageable, but when you're trying to distinguish between 13.7 and 14.5 billion years, small issues become very important. It is like trying to weigh a feather while standing on a moving train, except the feather is an ancient star, and the train is the history of astrophysics. This does not mean astronomers can choose any age they like. The star's properties are real constraints. HD 140283 is a subgiant, and that matters because subgiants are especially useful for age measurements. A star on the main sequence can remain fairly steady for a long time, especially if it is low mass. It can sit there burning hydrogen quietly while refusing to reveal exactly how long it has been doing so. A subgiant, however, has started to move away from that stable phase. Its brightness and temperature change more noticeably as its internal fuel situation shifts. That makes its position in the Hertzsprung-Russell diagram more sensitive to age. Methuselah is not simply old-looking in some vague way. Its stage of life gives astronomers a strong reason to measure its age carefully. The problem was that careful measurement led to a number almost as old as the universe, and perhaps a bit older if taken too literally. That kind of tension is not new in astronomy. Science has often moved forward through uncomfortable numbers. In the early 20th century there were debates about the age of Earth, the age of stars, and the timescale on which the sun could shine. Before nuclear fusion was understood, no known power source seemed able to keep the sun shining for billions of years. Later, measurements of the expansion of the universe and ages of old stars also had periods of tension. Sometimes the universe seems to hand us mismatched clocks, and the work is to discover which clock needs adjustment, or whether both are telling part of the truth in different ways. Methuselah became one of those clocks. It was not just a curiosity, it was a test. If the oldest stars are truly older than the universe, then either stellar physics is wrong, cosmology is wrong, or both need revision. That would be enormous. But if the oldest stars are very close to the age of the universe, and still slightly younger within uncertainties, then they support the standard picture. They tell us that star formation began very early, not long after the Big Bang, but not before it. The boundary is narrow and meaningful. A star like HD 140283 helps scientists ask when the first long-lived stars could have formed, how quickly the early universe cooled enough for star formation, and how soon the first supernovae enriched the gas with heavier elements. There is something almost dramatic in how undramatic the solution is. The answer is not that Methuselah came from another universe. It is not that it travelled backward through time. It is not secretly a loophole in cosmic history, wearing a small disguise in Libra. The answer is that the measurement was very difficult, the uncertainties were real, and the most careful interpretation keeps the star consistent with the age of the universe. The paradox softens when you respect the error bars. It does not vanish into boredom, though. The star remains extraordinary. In some ways, it becomes more extraordinary because the real story is not a gimmick. It is a precise object pushing our methods to their limits. A useful comparison is an old clock found in an attic. Suppose you find a clock that appears, from its design, materials and maker's marks, to be about 300 years old. But one part of the evidence suggests it might be 330 years old, while another historical record says the maker's workshop only opened 310 years ago. You do not immediately conclude that the clock was built before the workshop existed. You examine the evidence. Perhaps the wood came from an older source. Perhaps a repair changed the mechanism. Perhaps the maker's record is incomplete. Perhaps your estimate has a range. The clock is still old and valuable. The puzzle does not make it fake. It makes it interesting. Methuselah's age puzzle is similar. The star's low metal content says it formed early. Its high velocity says it belongs to an ancient galactic population. Its subgiant stage allows a good age estimate. Its proximity gives precise measurement. Everything points to great age. The only problem is how close the number comes to the universe's own age. Once astronomers account for the full uncertainty, the star no longer breaks the timeline. Instead, it tells us that the first generations of long-lived stars probably formed very soon after the universe became capable of making them. In other words, Methuselah is not older than the universe. It is one of the universe's earliest surviving children. That phrase, surviving children, may sound strange for a star more than 12 or 13 billion years old, but it fits the cosmic perspective. The first stars themselves were probably massive and short-lived. They burned hot and died quickly, enriching the gas around them. Methuselah formed later, from material that already contained small amounts of heavier elements. It was not one of the first stars ever, but it came from a very early era. It was low enough in mass to live a long time. Massive stars spend their fuel recklessly and die in millions of years. Smaller stars spend slowly. Methuselah was modest enough to last, and because it lasted, we can study it now. That survival creates a bridge between two very different kinds of evidence. Cosmology studies the universe as a whole. It looks at the microwave background, galaxy distributions, expansion, dark matter, dark energy, and the large-scale behavior of space. Stellar astrophysics studies individual stars, their interiors, chemistry, life cycles, and deaths. HD 140283 sits where those two fields meet. Its age estimate is a stellar measurement, but it has cosmological consequences. It says something about how early stars formed after the Big Bang. It gives an independent check on the age of the universe. It ties the small point of light in Libra to the whole history of space. This is why the mystery became so popular. It has all the ingredients of a good science story: a strange claim, a nearby object, a famous telescope, a number that seems impossible, and a resolution that teaches us how measurement really works. It also has a pleasing emotional shape. We begin with alarm, a star older than the universe. We move into investigation, distance, brightness, oxygen abundance, stellar models. We arrive at a calmer understanding, not impossible, but ancient beyond easy imagination. The result is less like a broken clock and more like a clock placed so close to the beginning that reading it requires very steady hands. There is another quiet lesson here too. The universe is not obligated to keep its most important truths far away. HD 140283 is only about 190 light-years from Earth, close enough to be part of our extended stellar neighbourhood. It is not in a distant galaxy, whose light has crossed almost all of cosmic history to reach us. Its light reaching us now is only a couple of centuries old. Yet the star itself is ancient. It is a local object with a deep time biography. That combination can feel almost intimate. The early universe is not only out there, at the edge of visibility. Some of its survivors pass relatively near us, moving through the Milky Way's old halo population, quiet and faint and easy to overlook. Imagine the star continuing on its path while human history rose and rearranged itself below. When early astronomers named Libra and drew scales in the sky, Methuselah was already old. When people built the first observatories, it was old. When telescopes were invented, it was old. When the Henry Draper catalogue recorded it, it was old. When Hubble measured its parallax, it was old. The star did not become ancient because we noticed it. We simply became capable of understanding how ancient it was. That is an important distinction. Science often feels like discovery, but for the universe it is more like being recognised late. Later studies have continued to refine the age of HD 140283. Some estimates, using updated modelling and additional observational constraints, place it lower than the famous 14.5 billion year figure. This is not a failure of the original story. It is part of the normal life of science. Better measurements arrive, models improve, assumptions are tested. The star remains old, metal poor and important, even if the exact best fit age shifts. The real value of Methuselah is not that one number must remain forever unchanged. The value is that it is a benchmark, a nearby ancient star that helps researchers test how well their models handle the earliest long-lived stars. There is a temptation, especially in public storytelling, to turn every tension into a crisis. A star older than the universe sounds more exciting than a star whose age estimate overlaps with the age of the universe once uncertainty is included. But the calmer version is actually better. It shows the universe as understandable but demanding. It shows science as flexible but disciplined. It shows that an apparent contradiction can be valuable even when it does not overturn everything. Sometimes the best mysteries are not the ones that destroy what we know, but the ones that force us to know it more carefully. So Methuselah did not break the universe. It tested our clocks. It asked whether the age of the cosmos, the physics of stars, and the chemistry of the early Milky Way could all fit together. And within the limits of current measurements, they do. The universe remains older than its stars. HD 140283 remains one of the great ancient survivors. The apparent paradox becomes a lesson in precision, patience, and humility. It tells us that when we measure deep time, we're often working near the edge of what our instruments and models can reveal. We can get astonishingly close, but we must carry the uncertainty with us. And perhaps that is not so different from how we experience time in our own small lives. We rarely know the exact age of a memory. We misplace dates. We compress years. We stretch certain moments until they seem larger than they were. Our own inner clocks are imperfect. Methuselah's cosmic clock is imperfect too, not because the star is confused, but because we are reading it from far away through physics, light, and models. Still, the broad truth is clear. This star formed early. It survived. It has spent almost the entire age of the universe shining quietly while galaxies grew, merged, and settled around it. If Methuselah is not older than the universe, but is still among its oldest known surviving stars, where did it come from? What kind of Milky Way was beginning to form when this star was born? What did our galaxy look like before its spiral disk became familiar? Before the sun, before Earth, before the night sky had anyone here to name it? By the time Methuselah began to shine, the Milky Way was not yet the calm, familiar-looking spiral we like to imagine from space paintings and telescope diagrams. There was no neat glowing disk with graceful arms curling outward like a slow pinwheel. There was no sun tucked into a quiet neighbourhood, no Earth circling patiently around it, no night sky with constellations waiting to be named. The galaxy was still young, uneven, and busy becoming itself. Gas was falling together under gravity. Small early star systems were merging. The first generations of stars had already begun changing the ingredients of space, but the galaxy had not yet been stirred into the rich mixture that would later form stars like our Sun. It was a rougher Milky Way, a younger Milky Way, a place where the building blocks of a future spiral were still being gathered, heated, torn, and rearranged. And somewhere in that early construction zone, from gas that had only recently been touched by the deaths of earlier stars, HD 140283 was born. Of course, Methuselah does not remember any of this in the way you or I remember a childhood street, a first bedroom, or the smell of dinner from a kitchen long ago. A star has no mind, no diary, no old photographs tucked into a drawer. It does not sit in Libra whispering, "Ah yes, the early halo years. Very dusty, terrible parking." But stars preserve information in their own physical way. Their chemistry remembers, their motion remembers, their mass, age, and path through the galaxy remember. Not consciously, but measurably. A star is a kind of object that can carry the conditions of its birth for billions of years, written into the atoms in its atmosphere and the orbit it follows through space. Methuselah's surface is not just a glowing outer layer. It is a record of the material from which it formed, and that material came from a much younger universe. To understand why this matters, picture the Milky Way not as a finished city, but as a settlement still under construction. Today, we live inside a broad stellar disk with spiral arms, gas clouds, dust lanes, star-forming regions, and an older halo surrounding it all like a loose, dim memory. But early on, the galaxy was assembled from smaller clumps of matter. Dark matter gathered first into invisible gravitational wells. Gas fell into those wells, heated, cooled, collapsed, and formed stars. Some of those early clumps merged with others, building larger structures. Over time, the Milky Way grew by swallowing smaller systems, drawing in gas and forming wave after wave of stars. It was not a tidy process. Galaxy formation is less like placing bricks in a wall and more like making soup while someone keeps adding ingredients, shaking the pot and occasionally dropping in another smaller pot. Methuselah likely belongs to the old halo population of the Milky Way. The halo is not where most of the bright familiar stars of the night sky belong. It is a vast sparse region surrounding the galaxy's disk, filled with old stars, globular clusters, streams, and traces of smaller systems that the Milky Way absorbed long ago. If the disk is the busy part of the galaxy where new stars still form from gas clouds, the halo is more like the archive. It is not empty, but it is thin and ancient. Many halo stars are poor in heavy elements, which tells us they formed early, before the galaxy had gone through many rounds of stellar birth and death. Methuselah's metal-poor composition and unusual motion fit that larger story. It is not moving like a typical younger star in the Sun's disk. It moves more like an old traveller from another layer of galactic history, passing through our neighbourhood on an orbit shaped long before the Sun existed. That motion is one of the reasons astronomers noticed it as unusual. HD 140283 is a high-velocity star, meaning it moves through our region of the galaxy at a speed and direction that set it apart from ordinary local disk stars. The Sun and many of its neighbours share the general rotation of the Milky Way's disk, like boats carried by the same broad circular current. Methuselah is different. It cuts through the local neighbourhood on a path that speaks of older galactic dynamics. Its light is slightly blue-shifted because it is moving toward us along our line of sight, and its proper motion across the sky has long marked it as a fast-moving object. That movement does not tell us its whole life story by itself, but it is a clue. In astronomy, a strange motion is often like seeing muddy boots at the door. It tells you someone has come from somewhere else. The chemistry tells an even deeper story. Methuselah has far less iron than the Sun. In astronomical language, it is metal poor, and once again, that word metal is doing the broad astronomy job where almost everything heavier than hydrogen and helium gets placed into one big category. This is one of those little scientific habits that sounds odd at first, and then becomes strangely convenient, like calling every item in a kitchen that is not flour or water seasoning. The reason it matters is that the Big Bang made mostly hydrogen and helium, with tiny traces of lithium. It did not make large amounts of iron, carbon, oxygen, silicon, calcium, or the other heavier elements that now fill planets and people. Those elements had to be made later inside stars. Some were made in stellar cores, some were made in supernova explosions, some were made in neutron-rich events and other violent processes. The universe had to cook before it could become chemically interesting. When Methuselah formed, there had not been much time for that cooking. Its gas cloud contained small amounts of heavy elements, so it was not made from the untouched original material of the Big Bang. That means Methuselah was not one of the first stars ever born. The very first stars, often called population 3 stars, are thought to have formed from almost pure hydrogen and helium. They were probably massive, brilliant, and short-lived. They lived quickly, died violently, and helped enrich nearby gas with the first heavier elements. Methuselah came after that. It is more like a second or very early later generation star, born from gas that had already been lightly enriched by earlier stellar deaths. It did not witness the very first instant of star formation, but it formed close enough to that era that its ingredients still carry the signature of a young galaxy. That is why Methuselah is so valuable. The Sun formed much later, from gas that had been enriched again and again over billions of years. By the time our solar system formed, the Milky Way had already produced many generations of stars. The gas that became the Sun contained enough heavy elements to make rocky planets, metal cores, water-bearing worlds, and eventually the chemistry of life. Methuselah's gas cloud was different. It was simpler, poorer, less seasoned, not empty of heavy elements, but sparse. The difference between Methuselah and the Sun is not just age, it is ancestry. The Sun was born in a galaxy already rich with the ashes of many stars. Methuselah was born when those ashes were rare. If we could somehow visit the Milky Way when Methuselah formed, which we cannot and probably should not, because early galaxies are not known for guest comfort, the view would be unfamiliar. The galaxy would likely have been smaller, more chaotic, and less settled. The thin disk we know today may not have fully formed. Gas clouds would have been assembling and colliding. Early massive stars would have been forming in bursts, shining fiercely, then dying quickly. Their explosions would send shock waves through surrounding gas, spreading newly made elements into nearby regions. Some gas would cool and collapse again, forming longer-lived low-mass stars like HD 140283. In that sense, Methuselah may have formed from material that had been enriched by only one or a few earlier events. That is why its composition can act like a fingerprint from the early Milky Way. A helpful way to think about this is baking bread from a starter. If you have a kitchen where the same starter has been used and refreshed for years, each loaf carries a history of what came before. The ingredients are not ancient in the same way the first flour was ancient, but the mixture has a lineage. With stars, the starter is interstellar gas. Each generation of stars changes it slightly. Massive stars add oxygen, magnesium, silicon, calcium, and other alpha elements. Supernovae add iron and many other products. Other stellar processes contribute carbon, nitrogen, heavy elements, and more. By the time a new star forms, the gas cloud has a chemical memory of all those earlier contributions. Methuselah's memory is short compared with the Sun's. Not short in years, of course, but short in generations. It seems to come from a time when only a few earlier stars had written on the gas. This helps explain why astronomers study its abundance pattern in such detail. They do not only ask, how much iron does it have? They ask how oxygen compares with iron, how carbon and nitrogen appear, what magnesium, calcium, and titanium are doing, and whether neutron capture elements such as barium and europium show particular patterns. These ratios reveal what kinds of earlier stars may have enriched the gas. A high abundance of some alpha elements compared with the iron can point toward enrichment by massive stars and their supernovae. Certain heavy element patterns can suggest rapid neutron capture processes. The details are complex, and scientists debate them carefully, but the basic idea is simple enough. Methuselah's atoms are clues to stars that died before it was born. There is something quietly astonishing about that. When we study HD 140283, we're not only studying HD 140283, we are studying its parents, or at least its chemical ancestors. Those earlier stars are gone. They burned out billions of years ago. We cannot point a telescope at them. We cannot watch their explosions directly. But they changed the gas from which Methuselah formed, and Methuselah has survived long enough for us to inspect that gas's altered recipe. In this way, an old star becomes a messenger from even older stars. It is not the first witness, but it carries testimony from witnesses that disappeared long before the sun was born. The early Milky Way was also a place of assembly. Some of the stars now in the halo may have formed in the main body of the young galaxy. Others may have formed in smaller dwarf galaxies or protogalactic fragments that were later swallowed. The Milky Way did not grow alone in a quiet room. It built itself by accreting smaller systems, pulling them apart with gravity and mixing their stars into its halo and outer regions. We still see evidence of this today in stellar streams, long ribbons of stars left behind by disrupted clusters and dwarf galaxies. Methuselah's exact birthplace is not something we can name with a street address, but its halo-like properties place it within that ancient assembly story. It may be a native of the early Milky Way, or it may have come from a smaller early system that became part of the Milky Way. Either way, it belongs to this era when our galaxy was still being built. That possibility gives the star a different kind of journey. It may have spent billions of years looping through the galaxy on an orbit very unlike the Sun's. It may have crossed through the disk many times. It may have moved far above and below the plane where younger stars form. It may have passed through regions that later became crowded with stars, then out into sparser halo space again. Human lives unfold across cities, rooms, roads, and weather. a halo star's life unfolds across gravitational fields. It follows a path shaped by the mass of the galaxy, by ancient mergers, by the dark matter halo around everything. It does not choose, it falls and orbits. But the path is still a history. While Methuselah travelled, the Milky Way changed around it. Gas settled into a disk, spiral structure developed and rearranged, new stars formed in great clouds. Some massive stars exploded and enriched the galaxy further. The chemical richness of the Milky Way increased. Planet-forming material became more common. Globular clusters aged. Dwarf galaxies were pulled in. The Sun eventually formed from a cloud that had been enriched by many earlier stellar generations. Earth formed. The Moon formed. Oceans gathered. Continents shifted. Life emerged. And through all of that, HD 140283 kept moving through the galaxy, faint and steady, not knowing that one day a species from a young rocky planet would use space telescopes and spectrographs to read its light. It is easy to imagine ancient stars as fragile, but Methuselah's survival is partly because it was never too massive. The early universe probably made many massive stars, but those did not last. They burned through their fuel quickly and died. A star like HD 140283, with less mass than the Sun, can live for an extremely long time. Its modest mass is its secret. Massive stars are the loud guests at the cosmic party, arriving brightly and leaving explosively. Low-mass stars are the quiet ones in the corner, who somehow remain after everyone else has gone home and the chairs are being stacked. Methuselah endured not because it was spectacular, but because it was restrained. It spent its fuel slowly. It let time pass. Now, as a subgiant, it has started to move away from the long stable phase of its life. That means its core hydrogen is largely exhausted, and its structure is changing. But even this change happens on timescales far beyond human intuition. A subgiant does not transform overnight. It is not suddenly old in the way a person may feel old after sleeping badly on the wrong pillow. The shift is slow, governed by gravity, pressure, fusion, and the deep interior balance of the star. The fact that we see Methuselah in this stage is useful, because it helps astronomers estimate its age more clearly. It is also a reminder that even the oldest survivors keep changing. Survival is not stillness, it is continued evolution. What does Methuselah remember from the young Milky Way? It remembers that the galaxy was chemically poor. It remembers that heavy elements were scarce. It remembers, through its orbit, a time before the disk became the dominant home of stars like the Sun. It remembers that the first stars had already begun to enrich space, but only lightly. It remembers a Milky Way assembled from smaller pieces shaken by mergers stirred by gravity and brightened by early bursts of star formation. It remembers all this without thought, because physics can preserve history without needing memory. That is one of the great beauties of science. The past is not gone completely. Some of it is stored in things, and those things do not have to be grand-looking. Again and again, Methuselah returns us to that quiet fact. It is not visually impressive through a small telescope. It doesn't dominate Libra. It does not glow with the obvious drama of a nebula or the clean ring of Saturn. But its small light contains an old galactic record. Astronomers can take that light, spread it into a spectrum and find the faint chemical marks of a universe not yet fully enriched. The star becomes a document, not paper, not ink, but plasma and photons. A document that has been travelling through the Milky Way since the galaxy's youth. This is why ancient halo stars are so important. They help us reconstruct the early Milky Way in a way that is different from looking at distant galaxies. Distant galaxies show us young galaxies as they appeared long ago, because their light has taken billions of years to reach us. Ancient nearby stars show us old survivors from early times, still present in our own galaxy. One method is like seeing a childhood photograph. The other is like speaking with an elder who lived through that childhood and still carries the marks of it. Neither method tells us everything. Together they give a richer picture. Methuselah in that sense is both local and ancient. Its light reaches us from only about 190 light-years away, but its composition points back to the beginning of the galaxy. It is a neighbour whose biography belongs to cosmic dawn. That combination is what makes it feel so strange and intimate. The early Milky Way is not only a distant idea, some of its surviving stars pass relatively near us. They cross the same broad galactic neighbourhood where our much younger sun now travels. They are not part of our solar system, of course, and 190 light-years is still an enormous distance by any human standard. But in the scale of the Milky Way, Methuselah is close enough to be studied with exceptional care. It is an ancient archive within reach of our instruments. As we follow this old star, the Milky Way begins to feel less like a static home and more like a long unfolding event. We live inside a galaxy that has a history. It was not always as it is now. Its stars have different ages, different origins, different chemical fingerprints. Some were born recently in spiral arms. Some belong to the thick disk, older and more vertically spread. Some belong to the halo, moving on ancient orbits that cut through the younger structure. Methuselah is one of those older wanderers, a survivor from the era when the galaxy was still assembling itself from gas, dark matter, and the remains of earlier stellar generations. And maybe that is the gentlest way to hold the thought tonight. Above us, the sky may look still, but it is filled with motion and memory. Stars are moving, galaxies are changing, elements are being made, scattered and gathered again. The Milky Way is not simply a place, it is a process that has been unfolding for more than 13 billion years. Methuselah is one small participant in that process, one that formed early enough to preserve a chemical trace of the young galaxy, and survived long enough for us to read it. When astronomers say that Methuselah is metal poor, they are not saying the star is missing a shiny surface, or that it somehow failed to pick up enough cosmic iron filings on its way through the galaxy. A star is not a warehouse shelf, after all, although if it were, HD 1 40283 would definitely be in the antique section, probably behind a small sign asking visitors not to touch anything. In astronomy, metal poor means something much broader and more important. It means that compared with the Sun, this star contains very small amounts of elements heavier than hydrogen and helium, and that simple fact turns its faint old light into a message from the early cosmos. Not a complete message, not one written in neat sentences, but a chemical record, a set of clues left behind by stars that lived and died before Methuselah was born. The reason this matters begins at the beginning, or at least very close to it. The early universe was chemically simple. After the Big Bang, space was filled mostly with hydrogen and helium, with just tiny traces of a few other light elements. There was no large supply of iron, no oxygen-rich worlds, no carbon chemistry drifting through thick clouds, no silicon rocks, no calcium bones, no gold rings tucked away in drawers, no copper wires carrying messages, no magnesium in green leaves, and certainly no complicated ingredients for people making tea while watching astronomy videos. The universe had the basic building blocks for stars, but not yet the rich periodic table we're used to. It had to make those heavier elements later, inside stars and in the violent events around stellar death. So when we look at a star like the Sun, we are looking at a relatively enriched object. The Sun formed about 4.6 billion years ago, long after earlier generations of stars had already fused lighter atoms into heavier ones and scattered them into space. The gas cloud that formed the Sun was not the universe's first plain hydrogen-helium mixture. It was seasoned by many earlier stellar lives. It contained enough heavy elements to form rocky planets, moons, asteroids, metal cores, water-bearing minerals, and eventually a small planet where living things would develop the curious habit of wondering what stars are made of. The Sun belongs to that later, richer chemical era. Methuselah does not. HD 140283 formed from a much poorer mixture. It contains iron, carbon, oxygen, magnesium, calcium, and other heavier elements, but in much smaller amounts than the Sun. That low abundance tells us that the cloud from which it formed had not been enriched by many previous generations of stars. The gas had only been touched lightly by earlier stellar activity. In other words, Methuselah was born when the universe had just begun to move from simple chemistry toward the more complicated chemistry needed for galaxies like ours. Its composition places it close to the era when the first stars had already started to change space, but before the Milky Way became a well-mixed reservoir of heavy elements. This is why metal-poor stars are so valuable. They're not just old because they have low metal content, and they're not low in metals simply because they are old in a vague sense. Their chemistry is tied to cosmic history. The first stars, the ones astronomers call Population 3, are thought to have formed from almost pristine hydrogen and helium. They would have been the first furnaces to make heavier elements in significant amounts. But those first stars were probably massive, hot and short-lived. They did not survive to the present day, at least not in the form we expect. They burned through their fuel quickly and died long before Earth existed. If we want to know what those earlier stars were like, we cannot simply point a telescope at one nearby and say, "Ah, there you are, thank you for waiting." They're gone, but they left traces. When those first massive stars died, they exploded or shed material, spreading newly made elements into surrounding gas. Later stars formed from that enriched gas. Some of those later stars were low mass enough to survive for billions of years. Methuselah is one of those survivors. It is not likely to be a first star itself because it contains heavy elements, but it may have formed from gas enriched by only a small number of earlier events. That makes it a kind of chemical witness. Its atmosphere contains hints about stars that are no longer around. It is like finding footprints in old snow after the traveller has disappeared beyond the trees. You cannot see the traveller, but you can learn something from the marks they left behind. The way astronomers read those marks is through spectroscopy. This is one of the great quiet miracles of science. Starlight arrives at a telescope as a tiny stream of photons after crossing many light years of empty space. To the eye, it may seem like a simple point, but when that light is spread into a spectrum, it becomes a rainbow filled with fine, dark lines. Those lines appear because atoms in the star's outer layers absorb specific wavelengths of light. Each element has its own pattern, its own little barcode. Hydrogen leaves one set of lines, calcium leaves another, iron leaves many, carbon, oxygen, magnesium, sodium, barium, europium, and others all leave their own clues if the observations are sensitive enough. For a metal-poor star, this work is especially delicate. Many of the lines are weak because the elements are scarce. Imagine trying to read a faded receipt left in the sun for several years, except the receipt is made of starlight, and the ink is atomic absorption. Astronomers need high-resolution spectra, careful calibration, and models of the star's atmosphere to turn those faint lines into abundance measurements. They must account for the star's temperature, gravity, turbulence, and the fact that atoms in a star do not always behave in the simplest possible way. Some analyses use corrections for non-local thermodynamic equilibrium, which is a very long phrase meaning roughly that the atoms are not always in the neat balance assumed by simpler models. The universe, once again, refuses to be tidy just because we are sleepy. One of the central measures astronomers use is called metallicity, often written as iron relative to hydrogen compared with the Sun. Iron is used as a convenient marker because it has many spectral lines and because it builds up over galactic history. HD 140283 has far less iron than the Sun, often described with a value around -2 or lower on this logarithmic scale. That may sound small if you're not used to logarithms, but it means the star has only a tiny fraction of the Sun's iron abundance. A value of -2 means about 1/100th of the solar iron level. A value lower than that means even less. Methuselah is therefore not just a little poor in iron, it is dramatically poor compared with the Sun. But iron is only part of the story. Different elements are made in different ways, and the ratios between them help reveal what kinds of earlier stars enrich the gas. Massive stars produce many so-called alpha elements, such as oxygen, magnesium, silicon, sulfur, calcium, and titanium, through nuclear fusion and supernova explosions. If an old star has relatively high alpha elements compared with iron, that can suggest that its birth cloud was enriched mainly by massive stars that died quickly, before slower sources of iron had much time to contribute. This is common in very old stars and is part of the chemical signature of the early galaxy. It tells us that the first enrichment was rapid, intense, and dominated by short-lived massive stars. Oxygen is especially important for Methuselah. It is not only important for life and water and all the familiar things that make oxygen feel friendly to us, it also affects estimates of the star's age and the models of how it evolved. The oxygen abundance helps determine how a metal-poor star behaves internally. Small changes in the oxygen measurement can shift the inferred age by meaningful amounts, so oxygen is both a chemical clue and a clock adjustment. It tells us about the star's birth material, and it helps astronomers decide how long the star has taken to reach its current subgiant stage. One element, quietly printed in a spectrum, becomes part of the answer to a cosmic age problem. Carbon and nitrogen also matter. Carbon is central to later chemistry, but in an ancient star it helps trace early nucleosynthesis. Nitrogen can reveal processing in earlier stellar interiors. The ratio of carbon isotopes, especially carbon-12 to carbon-13, can hint at what kinds of earlier stars contributed material to the gas. Studies of HD 1402, 83's carbon, nitrogen and oxygen have been used to test ideas about early galactic chemical evolution, including the possible influence of massive rotating stars or super-asymptotic giant branch stars in the early Milky Way. That may sound like a very specific family reunion, and in a sense it is. Astronomers are trying to identify the chemical relatives that came before Methuselah. They are not looking for names, but for processes. Then there are the heavier elements, the ones beyond iron. These are especially revealing because many of them are formed through neutron capture processes. In simple terms, atomic nuclei can capture neutrons and build up into heavier elements. There are different routes for this. The S process, or slow neutron capture process, happens over longer timescales in certain stars, especially evolved stars. The R process, or rapid neutron capture process, happens in much more extreme conditions where nuclei are bombarded with neutrons quickly. The exact astrophysical sites of the R process have been a major scientific question, with neutron star mergers now known to contribute, and certain types of supernovae or other explosive events also discussed in different contexts. In very old stars like Methuselah, heavy element patterns can tell us which processes had already begun operating in the early galaxy. HD 140283 has been studied in this context, because its neutron capture elements do not simply tell us that heavy elements existed. They tell us something about how the early universe made them. Some studies suggest that its heavy element pattern includes a strong R process contribution, with possible signs of what is called the weak R process for lighter heavy elements. That phrase does not mean the process was shy or lacking confidence. It refers to a pattern that may produce lighter neutron capture elements more effectively than the heaviest ones. These details are still studied and debated, but the broader point is clear. Even in the early Milky Way, the universe had already found ways to make elements far heavier than iron. Methuselah carries some of those traces. Think about the chain of events required for that to be true. First, the universe begins mostly with hydrogen and helium. Then, early stars form. Some become massive, they fuse elements in their cores. They explode or lose material, spreading heavier atoms into space. Gas clouds mix, though not perfectly. A new star forms from a small portion of that enriched gas. It is low mass enough to survive for almost the whole age of the universe. Billions of years later, that star passes near enough to the Sun for humans to study it. We build telescopes, we split its light, we measure tiny absorption lines, and from those lines we infer the lives of stars that vanished more than 13 billion years ago. It is a long chain, and every link is made of physics. There is something almost cozy about the fact that the periodic table has a history. We usually see elements as fixed entries in schoolroom charts, little boxes with symbols and numbers: hydrogen, helium, carbon, oxygen, iron. They seem so orderly there, like everyone politely seated at a wedding where no one spills soup. But in the universe, those elements have biographies. Hydrogen and helium come from the early hot universe. Carbon and oxygen are forged in stars. Iron is built in stellar cores and explosive deaths. Heavier elements can come from neutron captures in intense environments. The periodic table is not just a list, it is a record of cosmic labour. Methuselah's chemistry lets us read an early page of that record. Its poverty in metals is not a defect. It is the reason it is precious. A star with the Sun's rich composition tells us about a later galaxy, one already filled with recycled stellar material. A star like HD 140283 tells us about a time when that recycling had barely begun. It is like comparing a modern city street with an ancient settlement. The city has layers upon layers of construction, repairs, roads, pipes, cables, and signs. The settlement has fewer layers, fewer additions, and therefore preserves something closer to the beginning. Methuselah's surface has fewer chemical layers of galactic history, so its early clues are easier to see. There is also a question hidden in this. Why did Methuselah survive when so many earlier stars did not? The answer is mass. The first stars were likely massive, and massive stars live quickly. They burn fuel at a tremendous rate and die after millions of years. Low-mass stars burn slowly. HD 140283 had enough modesty, physically speaking, to last. It did not blaze itself into a quick ending. It carried its small chemical inheritance forward, through the growth of the Milky Way, through the birth of the Sun, through the formation of Earth, and all the way to telescopes capable of reading its faint lines. In cosmic history, survival often belongs not to the loudest objects, but to the ones that spend their energy carefully. Still, Methuselah is not chemically untouched. That is important. It is not pristine material from the Big Bang. If it were truly made only of hydrogen and helium, it would tell an even earlier story, but it would also be difficult to explain in its present form. The small amount of metals in HD 140283 shows that the universe had already been enriched before it formed. That means the first generations of stars had already done some of their work. This is why Methuselah is so useful. It sits in the narrow space between the first pure stars and the later chemically rich galaxy. It is early enough to preserve clues, but not so early that it lacks the evidence we need. When astronomers compare Methuselah's abundance pattern with theoretical yields from early supernovae, they are asking a kind of forensic question. What kind of explosion could have produced this mix? Was the gas enriched by one massive star or several? Were there fast-rotating massive stars involved? Did early asymptotic giant branch stars contribute certain elements? How quickly did neutron capture processes begin? How unevenly mixed was the early Milky Way? These questions are not easy because the early galaxy was messy. Gas clouds were not all perfectly blended. One region could be enriched by a nearby explosion, while another remained more primitive. The first generations of stars may have varied in mass, rotation, explosion energy, and chemical output. Methuselah's chemistry is one sample from that vast early complexity. That is why scientists do not rely on one star alone. They compare HD 140283 with other metal-poor stars, with stars in globular clusters, with stars in the halo, and with distant galaxies seen in their youth. Each object gives a clue. Together they help reconstruct the chemical evolution of the Milky Way. Methuselah is especially important because it is bright, nearby, and well studied. It serves as a benchmark, a reference point, a star whose abundance pattern can be examined with extraordinary precision. In a field where many ancient stars are faint and distant, a nearby one is a gift. Not a gift wrapped neatly, perhaps. More like a box full of spectral lines, stellar atmosphere corrections, and a note saying, "Some assembly required." The deeper meaning is that Methuselah's light connects us to stars that made the first heavy ingredients. The calcium in rocks, the oxygen in water, the carbon in living cells, and the iron in blood all belong to a universe that had to evolve chemically. Those atoms were not all present in the beginning. They came from stars and stellar deaths. Methuselah formed before that process had gone very far, but after it had begun. It is a reminder that the universe did not become habitable all at once. It had to build the conditions for planets and life over time. The first stars prepared the way. Later stars enriched the gas further. Eventually, much later, worlds like Earth could form. So when we look at HD 140283, we're not simply looking at an old star. We're looking at a record of cosmic preparation. Its metal-poor light says, "The universe was still young when I formed." Its oxygen and magnesium say, "Massive stars had already lived before me." Its iron shortage says, "Many later enrichment sources had not yet had time to add much." Its heavy elements say, "Even early on, extreme processes were already making complex nuclei." Its survival says, "A low-mass star can carry an ancient chemical message across almost the whole age of the cosmos." All of that is held in a faint point in Libra, a star too dim for unaided eyes, and yet bright enough for science to read. Perhaps the most remarkable part is that the atoms in Methuselah's atmosphere are not there for our benefit. They did not arrange themselves into clues because someday a telescope would need a bedtime story. They are simply the result of physical processes: fusion, explosion, mixing, collapse, gravity, radiation, and time. But human beings are pattern readers. We take the light and ask what came before it. We take the dark lines in a spectrum and turn them into history. We look at a metal-poor star and hear the echo of the first stellar furnaces. That is not because the universe speaks in words. It is because light preserves enough information for curiosity to translate. An old star does not leave its main life behind all at once. There is no dramatic morning when it wakes up, looks around the galaxy, and decides that hydrogen burning in the core has become a young star's game. The change is slower, quieter, and much more physical than that. Deep inside the star, after billions and billions of years, the central supply of usable hydrogen begins to run low. The core has spent almost the entire lifetime of the star doing the same basic work, fusing hydrogen into helium, releasing energy, and holding back gravity's inward pull. For a long time, that balance is steady enough that the star seems almost unchanging from the outside. It shines. It holds its shape. It keeps going. But no reservoir lasts forever, not even one measured on a timescale so long that all of human history would barely count as a late footnote. Eventually, the core changes, the balance shifts, and the star begins to move into a new stage. This is where Methuselah becomes especially useful, and also especially difficult. HD 140283 is not simply an old star sitting calmly on the main sequence, the long stable band where stars spend most of their lives. It is a subgent, which means it has started to leave that main phase behind. The hydrogen fuel in its core has mostly been used, and fusion begins to depend more on hydrogen in a shell around the growing helium core. The star's internal structure adjusts. Its outer layers respond. Its brightness and temperature begin changing in ways that tell astronomers it is no longer in the long, quiet middle of its life. This does not mean it is about to explode or vanish, so no need to clutch the blanket. For a low-mass star like Methuselah, these changes are slow. But they are real, and because they are real, they give astronomers a better chance to measure its age. A star on the main sequence can be frustratingly discreet about its birthday. Low-mass stars especially can sit there for billions of years, changing only gradually. If you look at one in the middle of that long stable life, its surface temperature and brightness may not tell you exactly how long it has been shining. It is a little like meeting someone who has looked roughly the same age for decades and refuses to mention when they were born. You can make a sensible estimate, but the range may be wide. A subgiant is different. Once a star begins leaving the main sequence, its properties change more quickly. Its luminosity starts to rise. Its position on the stellar life chart becomes more sensitive to time. It begins, in a sense, to show its age more clearly. That is why HD 140283 has been such an important object. It is old, nearby, metal poor, and in a stage of life where age can be estimated with unusual precision. Those qualities do not often come together so conveniently. Many very old stars are faint or distant. Many nearby stars are much younger. Some old stars are still on the main sequence and harder to date. Methuselah sits in a useful and strange place, close enough for detailed measurement, ancient enough to probe the early galaxy, and evolved enough that its current state gives real leverage on its age. It is almost as if the universe left an old clock on a table near us, not perfectly readable, not without scratches, but close enough for careful hands to inspect. Inside the star, the basic story begins with fusion. During the main sequence, a star balances gravity with energy from nuclear reactions in its core. Gravity tries to pull everything inward. Fusion produces pressure and heat that push outward. For most of a star's life, these two tendencies hold each other in a kind of deep physical truce. In Methuselah's case, because it is less massive than the Sun and poor in heavy elements, that truce lasted an extraordinarily long time. Smaller stars burn their fuel slowly. They do not rush through their lives the way massive stars do. A massive star may shine with great force and die after only a few million years, which is impressive, but not exactly a long-term plan. A lower mass star spends its fuel carefully, like someone making one cup of tea last through a very long evening. As hydrogen in the core is converted into helium, the core's composition changes. Helium builds up. The core becomes denser and hotter. Once there is not enough hydrogen left in the center for steady core hydrogen fusion, the star must adjust. Gravity contracts the central region. Hydrogen fusion continues in a shell around the helium core. Energy output changes and the outer layers expand somewhat. The star becomes a subgiant, moving away from the main sequence toward the red giant branch, though it has not yet become the large, cool giant it may one day be. This transition is slow by human standards, but quick compared with the star's long, stable life. That relative quickness is why the subgiant stage is so helpful for age measurements. Still, helpful does not mean simple. Methuselah is difficult because ancient stars are difficult in almost every useful way. First, they formed from unusual material. Their low metal content changes how they evolve. Heavy elements affect opacity, which is the way material inside a star absorbs and transports radiation. Opacity influences how energy moves outward, how temperature changes with depth, and how the star's structure develops over time. A metal-poor star is not just a sun-like star with fewer decorations. Its internal physics differs in important ways. So astronomers cannot simply take a solar model, subtract some iron in a casual afternoon and call it done. They need models built for the star's actual composition. Oxygen is one of the most important details. In a star like HD 140283, the amount of oxygen helps determine the evolutionary track and therefore the age estimate. A slightly different oxygen abundance can shift the predicted timing of the star's movement away from the main sequence. That is a delicate problem because measuring oxygen in a metal-poor star is not easy. The spectral lines can be weak. They can be affected by the star's temperature, surface gravity, and atmospheric conditions. Different lines may need different corrections. Astronomers must decide how best to model the star's atmosphere, whether simpler one-dimensional models are enough, and how non-local thermodynamic effects may change the result. This is where the quiet point of light becomes a great deal of work. Then there is diffusion. Over billions of years, atoms inside a star can slowly move under the influence of gravity, radiation, and mixing. Some elements may settle below the visible surface, others may be stirred back upward. This means the surface composition we measure today may not be exactly the original composition the star had when it formed. For an ancient star, that matters. If the surface iron, oxygen, magnesium, or other elements have shifted slightly over time, then models must account for that in order to reconstruct the star's birth composition and age. It is a little like trying to understand an old recipe after someone has quietly moved some of the spices to another shelf, then waited 13 billion years before telling you. Convection adds another challenge. Stars are not solid balls. Their outer layers can contain moving plasma, with hot material rising and cooler material sinking. This affects how heat is transported and how surface properties appear. In stellar models, convection is often handled using parameters that approximate a very complicated physical process. For the Sun, we can calibrate these parameters because the Sun is close and well observed. For an ancient metal-poor subgiant, the correct assumptions are less obvious. If the model treats convection slightly differently, the star's predicted temperature and luminosity at a given age may shift. Once again, small differences matter because Methuselah is being compared with the age of the universe itself. This is why the age of HD 140283 has been discussed, revised, and re-examined for years. The star is not difficult because astronomers are careless. It is difficult because it sits right at the edge where precision matters. If a star is clearly 5 billion years old, an uncertainty of several hundred million years is interesting but not alarming. If a star is estimated to be around 14 billion years old, the same uncertainty becomes central to the story. It can determine whether the star seems comfortably younger than the universe or slightly too old at first glance. Methuselah lives in that narrow zone where stellar physics, cosmic history, and measurement uncertainty all meet. The distance matters too. To know how far along the subgiant path Methuselah is, astronomers need its true luminosity. To know its true luminosity, they need its distance. Parallax measurements, especially those refined by the Hubble Space Telescope, helped enormously. Better distance means better brightness. Better brightness means better placement on the Hertzsprung-Russell diagram, where stars are arranged by luminosity and temperature. Once placed there, Methuselah can be compared with theoretical tracks for stars of different masses, ages, and compositions. But even with excellent distance, the age still depends on the models and measured chemical abundances. The star is close enough to help us, but old enough to keep some secrets. There is also the problem that we cannot watch a star age in real time. Human lives are much too short. We cannot observe Methuselah for a few million years and say, "Ah yes, there it goes, moving nicely along the subgiant branch." We see one moment in its enormous life. To understand that moment, we compare it with theory and with other stars. It is the same reason you can understand that an acorn, a sapling, and an oak tree represent different stages of one kind of life, even if you do not personally watch one tree for centuries. Astronomers build stellar evolution models to provide that sequence. They calculate how stars of a given mass and composition should change over time, then place real stars into that framework. For old field stars like Methuselah, there is another missing convenience: a family. In a star cluster, many stars are born at roughly the same time from the same cloud. This gives astronomers a group to compare. The most massive stars leave the main sequence first, and the turn-off point tells the cluster's age. Methuselah is not in such a neat family portrait. It is an individual halo star moving through the solar neighbourhood. That means its age must be inferred from its own properties, rather than from a surrounding population of siblings. Field stars are more solitary as evidence. They can still be understood, but they demand more careful reconstruction. The oldest stars are hard to understand for another reason. They are rare survivors of a vanished environment. The early Milky Way was not like the Milky Way today. Its gas was poorer in heavy elements. It had been enriched unevenly by earlier stars. It was still assembling through mergers and flows of gas. A star born in that environment may carry a chemical mixture unlike anything forming now near the Sun. Our models of stellar evolution are strong, but they must be tested against stars formed under conditions we cannot reproduce in a laboratory. We cannot create a baby Methuselah in a tank, wait 13 billion years, and compare notes, which is probably just as well since the grant proposal would be difficult to schedule. So astronomers use every clue available. They measure the star's temperature from its colour and spectrum. They measure its surface gravity, which tells them how strongly gravity acts at the visible surface. They measure its chemical abundances. They measure its distance. They estimate its mass by comparing it to models. They include diffusion, nuclear reaction rates, and assumptions about convection. They test whether the model fits the star's observed properties. They check whether the age makes sense alongside the age of the universe and other old stars. Every number is connected to another number. It is less like reading a clock and more like solving a very old, very faint crossword puzzle, where the clues are written in absorption lines. Even the phrase "leaving its main life behind" needs a little care. Stars do not have purposes or careers. The main sequence is not a job they retire from with a small cake in the break room. It is a physical phase, and leaving it means the internal fuel arrangement has changed. But the phrase works because the main sequence is where a star spends the majority of its life. For Methuselah, that main life lasted across most of cosmic history. While galaxies formed and merged, while the Milky Way developed its disk, while the Sun and Earth appeared, Methuselah was still in or near its long, stable phase. Now it is shifting onward. It is not finished, but it is no longer in the same internal state that carried it through the deep past. The coming stages will change it further. As the helium core contracts and hydrogen shell burning continues, the star will eventually become a red giant, expanding and cooling at the surface while growing much brighter. Later, for a low-mass star, the outer layers may be lost, and the remaining core may become a white dwarf. But these events are not immediate. Methuselah's life still unfolds on astronomical timescales. The star is old, but old does not mean done. It is more accurate to think of it as a long-lived traveller entering a later part of the road. The pace is slow enough that, from our point of view, it seems still, but inside the physics has already begun to turn. This slow change gives the star its scientific value and its quiet, emotional pull. Methuselah is ancient, but it is not a fossil in the strict sense. A fossil is dead, a preserved remnant. D140283 is still active, still glowing, still transforming. It carries evidence of the early cosmos, but it is not trapped there. It belongs to the present too. The light reaching us now was emitted recently in cosmic terms, after the star had already survived nearly everything needed for our solar system to exist. That recent light comes from an ancient object in a later stage of life. It is a living record if we use the phrase gently and not biologically. It is both archive and process, and perhaps this is why the oldest stars are so hard to understand. They ask us to combine many kinds of time at once. There is nuclear time, measured by fuel burning in a stellar core. There is chemical time, measured by how enriched the galaxy had become when the star was born. There is galactic time, measured by orbits through the halo and the growth of the Milky Way. There is observational time, measured by the light crossing 190 years to reach us. And there is human time, measured by the decades over which astronomers refine their models and argue politely with error bars. Methuselah sits at the intersection of all these clocks. The reward for that difficulty is enormous. By understanding one old subgiant, astronomers can test stellar physics near the earliest ages of the galaxy. They can compare star ages with the age of the universe. They can study how quickly the first long-lived stars formed after the Big Bang. They can investigate how the early Milky Way was enriched by the first supernovae. They can refine models that apply not only to Methuselah, but to other old stars and clusters. One faint star becomes a benchmark for a whole field of questions. That is a lot of responsibility for a point of light that most people need binoculars to see. There is a gentle irony here. Methuselah helps us understand ancient stars precisely because it has stopped being perfectly ordinary. If it were still sitting quietly in the deepest part of its main sequence life, its age would be harder to pin down. Because it is leaving that stage. Because its structure has begun to change, it reveals more. The signs of aging are not just decline, they are information. In a star, the beginning of the later life becomes a clue to the length of earlier life. The subgiant stage is the star's way of letting the past show through the present. As we watch Methuselah, or rather measure it from far away, we're catching a transition that has been billions of years in the making. The star was born when the galaxy was young. It carried metal-poor chemistry from the early cosmos. It survived through the formation of the Milky Way's later structures, through the birth of the Sun, through the entire history of Earth. Now its core has changed enough that its outer appearance is shifting. That shift lets us read its age with more confidence, but it also reminds us that even the oldest survivors are not fixed. They continue to evolve, quietly and steadily, according to the same physics that shaped them from the beginning. One of the quietest ways to test the age of everything is to look for the oldest thing still shining. That may sound almost too simple at first. If you want to know how old the universe is, surely you should look outward to the farthest galaxies, or study the afterglow of the Big Bang, or measure how quickly space itself is expanding. And astronomers do all of that. They use the cosmic microwave background, galaxy surveys, supernova, expansion rates, dark matter models, and a whole toolkit of measurements with names that sound as if they were designed to make a sleepy person reach for a blanket. But there is another kind of clock too, quieter and closer to home. A clock made of stars. Not ticking, not chiming, not sitting politely on a bedside table, but burning slowly through nuclear fuel and carrying its age in its light. Ancient stars help us test the age of the universe, because they set a lower limit. The idea is wonderfully direct. The universe must be older than the oldest stars inside it. A star cannot be born before there is space, matter, gravity, and time enough for gas to collapse and ignite. So if astronomers find a star that is 12.5 billion years old, the universe has to be older than 12.5 billion years. If they find a globular cluster of stars around 13 billion years old, the universe has to be older than that cluster. These old objects do not give the full story by themselves because the universe existed before they formed. There had to be time after the Big Bang for matter to cool, for gas to gather, for the first stars to ignite, for early explosions to enrich space, and for later long-lived stars to form. But they give a very important flaw. They say, whatever else your cosmology claims, the universe cannot be younger than this. That sounds neat. But of course, the universe is not in the habit of making neatness too easy. Measuring the age of an ancient star is hard. Measuring the age of the universe is also hard. The beauty comes when the two difficult measurements agree. When cosmology says the universe is about 13.8 billion years old, and the oldest stars and globular clusters come out slightly younger, within their uncertainties something important happens. Two very different methods point toward the same broad timeline. One method looks at the universe as a whole, the expansion of space, and the ancient radiation left from the early hot cosmos. The other method looks at individual stars and star clusters, using nuclear physics, brightness, temperature, chemistry, and stellar evolution. If those two clocks match, even roughly, we gain confidence that our picture of cosmic history is not wildly wrong. Methuselah HD 140283 is one of those old stellar clocks. It does not tell the age of the universe directly. It does not contain a miniature Big Bang calendar in its core, although that would be convenient and would probably make telescope proposals much shorter. What it does is test whether the earliest long-lived stars fit into the universe's known timeline. Its age estimate once seemed uncomfortably high, close enough to the age of the universe that it became famous. But once measurement uncertainties are treated honestly, it does not truly break the cosmic clock. Instead, it becomes a powerful check. It tells us that a low-mass, metal-poor star could have formed very early, soon after the first generations of stars began enriching the young galaxy, and could still be shining today. That is why ancient stars are so useful. They are independent witnesses. The cosmic microwave background is like a baby picture of the universe, taken when space was only about 380,000 years old and cool enough for light to travel freely. From that early radiation, scientists can infer the contents, shape, expansion history and age of the universe. Ancient stars are different. They are not baby pictures. They are survivors. They formed later, after the first gas clouds collapsed into stars, and they have lasted long enough for us to examine them in the present. If the cosmic microwave background is the universe's earliest photograph, ancient stars are like elders still sitting in the room, carrying physical traces of the past in their bodies. The comparison is not perfect, of course. Stars are not people. They do not remember consciously. They do not tell stories over tea, though if Methuselah could tell stories, one suspects it would begin very slowly and occasionally correct our pronunciation of metallicity. But stars preserve information through physics. Their chemistry reveals the conditions of the gas from which they formed. Their brightness and temperature reveal where they are in their life cycle. Their mass tells us how quickly they burn through fuel. Their movement tells us whether they belong to the disk, halo, or another ancient component of the galaxy. Put all of this together, and an old star becomes a physical record of an early era. Globular clusters are another major piece of the age puzzle. These are dense, spherical collections of stars, often containing hundreds of thousands of members, orbiting in and around galaxies like ancient swarms of light. Many globular clusters are extremely old. Because their stars formed roughly together, astronomers can estimate the cluster's age by studying which stars are still on the main sequence and which have already moved away from it. Massive stars burn out first. Smaller stars last longer. The point where stars turn off from the main sequence acts like a clock. If only lower mass stars remain on the main sequence, the cluster must be old. If higher mass stars are still there, the cluster is younger. It is a little like estimating how long a candlelit dinner has been going by seeing which candles have already burned down. Except the candles are stars. The dinner lasts billions of years, and nobody remembered to bring dessert. White dwarfs offer yet another kind of clock. A white dwarf is the hot, dense core left behind after a star like the Sun sheds its outer layers near the end of its life. Once formed, a white dwarf no longer produces energy through fusion in the usual way. It cools slowly over time, fading like an ember. By measuring the temperatures and brightnesses of the faintest white dwarfs in an old star cluster, astronomers can estimate how long they have been cooling, and therefore how old the cluster must be. This is a very different method from main sequence turn-off dating, which makes it valuable. When several independent stellar clocks give similar answers, it becomes harder to dismiss the result as a coincidence. There is also nucleocosmochronology, which is a very large word for using radioactive elements as clocks. Certain heavy elements decay at known rates. If astronomers can measure the abundance of radioactive elements such as thorium or uranium in very old stars and compare them with stable elements, they can estimate how much time has passed since those elements were made. This method is difficult because the initial amounts must be estimated, the spectral lines can be weak, and the production of heavy elements in early cosmic events is complicated. It is not the easiest clock to read. It is more like finding an ancient hourglass with some of the sand missing and trying to decide how much was in it at the start. Still, when it works, It offers another independent way to probe deep time. All these clocks matter because the history of cosmology has not always been comfortable. There were times when estimated ages of stars and clusters seemed to conflict with estimated ages of the universe. In the past, some calculations of the universe's expansion suggested a universe too young to contain its oldest stars. That was a serious tension. If your model says the house is 8 billion years old, but the furniture inside it is 12 billion years old, something in your model of the house needs attention. Over time, better measurements of stellar distances, better understanding of stellar physics, and improved cosmological observations helped resolve much of that tension. The universe became older in the calculations, and the oldest stars became better understood. The clocks moved into better agreement. Methuselah belongs to this tradition of useful tension. Its famous age estimate did not destroy cosmology, but it did remind scientists how carefully stellar ages must be measured. It pushed attention toward distance, oxygen abundance, stellar models, diffusion and uncertainty. It showed that a single old star can sit near the edge of the universe's age and still be consistent with it, provided the error bars are respected. In science, that phrase is not a small footnote. It is a guardrail. Without uncertainty, numbers can sound more certain than they deserve. With uncertainty, they become honest tools. Ancient stars also test the timing of early star formation. The universe was not full of stars immediately after the Big Bang. At first, it was hot, dense, and filled with particles and radiation. Later, after the first atoms formed, there was a long period before the first stars lit up. Gravity had to gather matter into dense regions. Gas had to cool and collapse. Dark matter helped shape the first structures. Eventually, the first stars formed, probably massive and short-lived. They changed the universe by producing the first significant heavy elements. Then later generations of stars formed from enriched gas. Methuselah, with its small but real metal content, belongs after that first enrichment. Its great age tells us that this whole sequence must have happened early enough for a low-mass star to form and survive until now. That is a powerful constraint. If a star like HD 140283 is more than 13 billion years old, then the first enrichment and the formation of low-mass stars in the early Milky Way, or in the smaller systems that helped build it, must have occurred fairly soon after the universe began. Not instantly, but early. The star becomes a timestamp for the young galaxy. It says, by this point the universe had already made heavier elements, mixed them into gas and formed stars small enough to last. That is not a small statement. It connects one faint subgiant in Libra to the first generations of light. The age of the universe from cosmology and the ages of the oldest stars do not answer exactly the same question. Cosmology asks, how long has the universe been expanding from its early hot state? Stellar ages ask, how long has this star or cluster existed since it formed? There should be a gap between those numbers, because stars formed after the universe began. If the oldest stars are just a little younger than the universe, that tells us star formation began very early. If they were much younger, that would suggest a longer delay. If they seemed older, that would point to a problem in the measurements or models. In this way, ancient stars help us understand not only the total age of the universe, but the schedule of its first major events. This is especially important now that telescopes can see very distant galaxies from surprisingly early times. The James Webb Space Telescope has found galaxies that existed only a few 100 million years after the Big Bang. These observations show that structure formation in the early universe was active and perhaps more efficient or complex than some simple expectations suggested. Ancient stars in our own galaxy offer a complementary view. Distant galaxies show us early cosmic history directly through old light. Nearby ancient stars show us surviving evidence from early cosmic history through old objects. One is a look across space and time. The other is a careful reading of fossils still present nearby. There is a pleasing balance in that. To understand the age of the universe, we look both outward and inward, both far away and close to home. We study the oldest light in the universe, stretched into microwaves across all space. We study distant galaxies whose light began travelling when the cosmos was young. We study old clusters around the Milky Way. We study faint white dwarfs cooling in the dark. We study metal-poor halo stars passing through the solar neighbourhood. Each method has its own difficulties, each has its own assumptions, but when they begin to agree, they create a stronger story than any one method alone. A useful way to imagine it is a courtroom, but a very calm one, with less shouting and more chalk. The age of the universe is the question before the court. The cosmic microwave background gives one testimony, the expansion rate gives another. Ancient globular clusters stand up and say, "We've been here for about 13 billion years." White dwarfs say, "We have cooled for this long." Metal-poor stars like Methuselah say, "We formed when the galaxy was young, and our chemistry proves it." The judge, who is probably a very patient statistician, listens to all of them and looks for consistency. No single witness has to be perfect. The strength comes from the pattern. Methuselah's role is special because it is an individual star in our neighbourhood. Globular clusters provide group ages, but HD 140283 lets astronomers study one ancient star in detail. Its distance, brightness, temperature, chemical composition, and evolutionary stage have all been measured carefully. Because it is a subgiant, its age is more accessible than that of many main sequence stars. Because it is metal-poor, it links to the early universe. Because it is nearby, its measurements can be more precise than those of many ancient stars farther away. It is not the only old star, and it may not hold a simple permanent title as the oldest, but it remains one of the best-known ancient benchmarks. The word benchmark is useful here. A benchmark is not just a record holder, it is something used to test other things. Methuselah helps test stellar evolution models. If models cannot explain a well-observed metal-poor subgiant without making it older than the universe, then the models need refinement. If changes in oxygen abundance, diffusion or distance bring the age into agreement, then the models become more credible. The star also helps test the connection between stellar physics and cosmology. It asks whether our understanding of small-scale nuclear burning and large-scale cosmic expansion can coexist peacefully. So far, with careful uncertainties, they can. There is a deep humility in this. We are trying to measure the age of everything using clues from light that reaches a tiny planet orbiting a middle-aged star. Our instruments are brilliant but not magical. Our models are powerful but not complete. Our numbers are precise, but only within ranges. Ancient stars remind us that the universe can be known but not bullied. We cannot demand that Methuselah give us a perfect age. We can ask better questions, improve the measurements, and let the answer sharpen over time. That is a very different attitude from pretending certainty where none exists. It is slower, but it is stronger. Maybe that is why the story feels right for a quiet night. The oldest stars do not rush. They have spent billions of years shining while galaxies formed, planets gathered, and life appeared in at least one small corner of space. They ask us to slow our own thinking too, to accept that cosmic truth is assembled from many measurements, to appreciate agreement when it appears, to understand that a number like 13.8 billion years is not just a fact drop from the sky, but the result of many lines of evidence converging. The universe has an age not because someone guessed boldly, but because many clocks, cosmic and stellar, have been read carefully. And those clocks are still being read. New observations improve distances. New stellar models refine ages. New surveys find more metal-poor stars. Astroseismology lets astronomers listen to stellar interiors. Better spectra reveal weaker chemical lines. Space telescopes push deeper into the early universe. Even disagreements can be useful, because they show where our understanding needs work. Methuselah's apparent age problem was not a failure. It was a signpost. It pointed toward the precision needed when measuring objects nearly as old as time itself. So ancient stars help us test the age of the universe, not by giving one simple answer, but by standing as witnesses against impossible timelines. They say the universe must be older than us. They say early star formation happened quickly. They say the first heavy elements were made soon enough to enter later stars. They say the Milky Way began assembling its old populations near the dawn of cosmic history. And when their ages line up with the age inferred from the cosmic microwave background, they give us a more complete confidence that the universe's great clock is being read correctly. Methuselah, faint in Libra, belongs to this family of cosmic clocks. It is not a loud clock. It does not tick in a way we can hear. It burns, shifts, and slowly evolves. Its age is read through distance, luminosity, chemistry, and models. Its usefulness comes from being close, old, metal poor, and just evolved enough to reveal its timeline. In its quiet way, it helps hold the universe accountable, not by challenging the Big Bang, but by confirming that the story must make room for stars like it. Ancient survivors born very early, yet still younger than the cosmos that made them. And so we come back gently to that faint point of light in Libra. Not a great beacon, not a star that dominates the sky, not a dazzling object that forces every eye upward the moment night arrives. Just a small old star, modest in appearance, easy to miss, and yet carrying one of the longest stories we have ever learned to read. Methuselah, HD 140283, has followed us through questions of distance, chemistry, motion, age, and the early Milky Way, and now it leaves us with something quieter than a puzzle and larger than a fact. It leaves us with a feeling for time, not just time as a number, not just time as something divided into seconds and calendars and phone alarms that always seem to arrive a little too confidently, but time as a deep physical history, something written into starlight, into atoms, into the slow life of a galaxy, and into the small human moment in which we notice it. When we began, Methuselah seemed almost impossible. A star so old it once appeared to press against the age of the universe itself. That idea had a wonderful kind of strangeness to it, the kind that makes you pause and look twice. Could a star really be older than the universe? Of course, the careful answer is no. The universe must come first. Space, matter, gravity, and time must exist before a star can gather itself from gas and begin to shine. But the fact that Methuselah came close enough to make the question feel serious is part of what makes it so valuable. It did not break the universe, it made us check our clocks. It asked astronomers to measure its distance more carefully, to understand its oxygen and iron more precisely, to refine models of old metal-poor stars, and to remember that deep time is not read with a single number, but with many pieces of evidence, each with its own uncertainty. That may be one of the most comforting things science teaches when we let it speak slowly. A mystery does not have to destroy what we know in order to matter. Sometimes a mystery matters because it sharpens what we know. Methuselah did not overturn cosmology. It strengthened the conversation between stellar physics and the age of the universe. It reminded us that the oldest stars are not just decorations in the night. They are clocks, records, witnesses, and tests. Their light helps confirm that the universe is old enough to contain them. Their chemistry helps reveal how early stars lived and died. Their motion helps trace the early structure of the Milky Way. Their survival shows us that some quiet things endure across almost unimaginable spans of change. Think for a moment about everything that has happened since Methuselah first began to shine. The Milky Way was still young. Its disk had not yet become the settled home that later gave birth to the Sun. Smaller systems were merging. Gas clouds were collapsing. Massive early stars were dying and scattering the first heavier elements into space. The universe was still chemically poor, still learning, in a physical sense, how to become complex. Methuselah formed from gas that had only been lightly enriched by those earlier stars. It carried into its body a small amount of iron, oxygen, carbon, magnesium, calcium, and other elements, not enough to resemble the Sun, but enough to show that something had already happened before it. Before Methuselah, other stars had lived. Before our Sun, Methuselah had already grown old. Before Earth, before oceans, before cells, before forests, before anyone looked upward and gave names to constellations, that faint star was already crossing the galaxy. It is difficult to hold that timescale in the mind. We can say 13 billion years, or 14 billion years, and the words pass easily enough. They fit in a sentence. They sit quietly on the page. But the meaning is too large to grasp all at once. Human beings are built for days and seasons, for meals and sleep, for birthdays and memories, for the soft, manageable rhythm of a life. A billion years is not a large version of a year in the way a mountain is a large version of a stone. It is something else entirely. It is time enough for planets to form and cool, for atmospheres to change, for continents to drift, for life to appear and transform a world. Methuselah has lived through many such spans. It has been there while whole classes of stars were born and died, while galaxies changed shape, while the material that would one day become us was slowly prepared in the furnace of cosmic history. And yet the star itself is not grand in the way we often expect ancient things to be grand. It is not huge. It is not young and bright. It is not wrapped in a colourful nebula or roaring toward a dramatic explosion. It is a subgent, slowly leaving the long, stable part of its life behind. Its core has changed. Its hydrogen story is moving into a later phase. Its outer layers are responding to what has happened deep inside. It is old, but not finished. That is an important detail. Methuselah is not a dead relic. It is still shining. It still belongs to the present. The light we receive from it left only about 2 centuries ago, recent by cosmic standards. Even though the star producing that light is ancient almost beyond comparison, its light is young, its body is old, its chemistry is older still in meaning, because it points to stars that came before it. In that layered way, Methuselah teaches us that time is not one simple thing. It can be distance, age, memory, motion, and change all at once. There is also a lesson in its metal-poor light. The atoms in Methuselah tell us that the universe was not born ready for planets like Earth. It had to become ready. The Big Bang gave the cosmos mostly hydrogen and helium. The first stars had to ignite before heavier elements could become common. Those stars had to fuse atoms in their cores and scatter new material into space through powerful deaths. Later stars had to form from that enriched gas. More stars had to live and die. The galaxy had to grow richer over time. Only after many generations could there be enough carbon, oxygen, silicon, iron, and all the other familiar ingredients for rocky planets, water, and life. Methuselah formed near the early part of that process. It is a reminder that home was not immediate. Home was prepared. That thought can be surprisingly tender. Earth feels solid and ordinary beneath us. The sun rises with such reliability that we rarely think of it as a late arrival in a very old story. The air feels like air. Water feels like water. A stone feels like a stone. But all of these things depend on a universe that spent billions of years making ingredients. Every familiar object has a cosmic ancestry. The iron in a tool, the calcium in bone, the oxygen in a breath, the carbon in a living cell, the silicon in a grain of sand, all of it belongs to a history of stars. Methuselah's poverty in those elements helps us understand how precious their later abundance became. It shows us the universe before the recipe was fully seasoned, before the kitchen was stocked, before the table was set. And somehow, from that early simplicity, the long chain of events eventually led to this moment, to you listening, to a voice speaking softly about an old star, to a planet that can wonder about its own origins. Methuselah also teaches us about humility. For a while, its estimated age seemed to create a problem. the star appeared older than the universe. It would have been tempting to turn that into a loud claim, to say everything we know must be wrong, to wave the paradox around like a flag. But the real story was more patient. Scientists checked the distance, they improved the parallax, they studied the spectrum, they examined oxygen, iron, diffusion, stellar models and error bars. The paradox softened, not because it was ignored, but because it was treated carefully. That is a very good lesson, not only for astronomy, but perhaps for thinking in general. The first surprising number is not always the final truth. The best answer often arrives through correction, refinement, and the willingness to say, let us look again. In a world that often rushes towards certainty, an ancient star asks for patience. It asks us to respect the difficulty of knowing. It asks us to let precision be beautiful. There is beauty in a dramatic image of a nebula, yes. There is beauty in Saturn's rings, in a total eclipse, in a galaxy seen edge-on like a blade of light. But there is also beauty in a tiny shift of parallax measured by a space telescope, in a faint oxygen line in a spectrum, in the careful placement of a star on a diagram, in the quiet phrase, within uncertainty. These are not dull details. They are the way the universe allows itself to be understood. Methuselah's story is built from such details, and because of them, we can say with real confidence that this faint star is one of the oldest stellar survivors we know. Maybe that is why it feels so fitting that Methuselah is not visible to the naked eye for most of us. Its importance is not obvious. It must be sought. It must be measured. It must be listened to in the language of light. Many things in the universe are like that. Their meaning is not on the surface. A faint dot may be a galaxy. A dark line in a spectrum may reveal an element. A small difference in brightness may show a planet crossing a star. A tiny timing shift may reveal gravity-bending space. The universe is not always loud. Often it is exact. Often it is quiet enough that only careful attention finds the story. And what a story this star gives us. It tells us that the Milky Way has a childhood, that our galaxy was not always the familiar river of light we see from dark skies. It was assembled from gas, dark matter, and smaller systems. It formed stars, lost stars, swallowed smaller companions, built a disk, enriched itself, and kept changing. Methuselah moved through that history. It belongs to an older population, likely connected with the halo, that wide and ancient component surrounding the younger disk. It does not orbit the galaxy like the Sun does. It passes through our region as an old traveller, carrying a path shaped by early galactic events. Its motion is part of the record. Its chemistry is part of the record. Its age is part of the record. In one faint star, the young Milky Way still has a traceable survivor. There is a strange comfort in knowing that old things remain near us. The early universe is not only far away at the edge of telescopic sight. Some of it is here, in our own galaxy, in ancient stars moving through the solar neighbourhood. Methuselah is not close by human standards, of course. About 190 light-years is still an enormous distance. But in a galaxy 100,000 light-years wide, it is nearby enough to feel almost neighbourly. It is as if a piece of the Milky Way's earliest memory has wandered within reach of our instruments. Not within reach of our hands, but within reach of our questions. And sometimes that is enough. As we think about time, origins, and home, Methuselah offers a gentle rearrangement of perspective. We often imagine home as something fixed, a house, a room, a street, a town, a planet. But our deeper home is moving. Earth orbits the Sun. The Sun orbits the Milky Way. The Milky Way moves within the local group. Galaxies drift in expanding space. Nothing is truly still. Even Methuselah, ancient as it is moving. Home is not a fixed point in a motionless universe. Home is a relationship, a temporary arrangement of matter and light, held together long enough for life to look around. That does not make it less real. If anything, it makes it more precious. A home that exists inside motion is still home. A moment that exists inside deep time is still a moment. The oldest starlight also reminds us that we arrive late, but not too late. We missed the first stars. We missed the birth of Methuselah. We missed the early assembly of the Milky Way. We missed the formation of the sun by billions of years, and we will miss much of the future. That might sound sad if said too sharply, but said gently, it becomes something else. We arrive exactly where we can. We live in a universe old enough to have made the ingredients for us, but not so old that all stars have gone dark. We live after the first enrichment, after planets became possible, after life found a foothold, and before the long future has taken away the sky. We are temporary, yes, but we are temporary at a remarkable time. And now, dear listener, as this journey settles, perhaps you can let Methuselah become not just a fact to remember, but an image to rest with. Somewhere in Libra, beyond ordinary sight, an ancient star continues to shine. Its light crosses the dark between stars and reaches our telescopes. Its atoms tell of a young universe, of first stellar deaths, of gas enriched just enough to form a long-lived survivor. Its age presses close to the beginning without breaking the story. Its existence helps us test the universe's clock. It is not dramatic in the sky, but it is immense in meaning. A faint old star still shining after almost everything we know had to happen around it. So let me ask you one last time, softly, where are you listening from tonight? What time is it in your little part of the world? Maybe the clock beside you has moved farther than you expected. Maybe your room has grown quieter. Maybe your thoughts are beginning to loosen around the edges, as if the day itself is becoming a little less solid. And perhaps that is a good place to leave this old star for now, not with a sudden ending, but with the sense that its story continues whether we are awake to hear it or not. The sky remains above us. The galaxy keeps turning. Methuselah keeps moving through the Milky Way, old, faint, patient and real. If this quiet voyage through ancient starlight gave you a little calm, or helped the universe feel a touch more familiar, I would be grateful if you liked the video, subscribed, or shared this sleepy corner of science with someone else who might enjoy a peaceful drift through deep time. The oldest stars do not ask us to hurry. They ask us to notice. They remind us that our lives are brief but not disconnected. We are made from a universe with a memory, and we live under a sky where some of that memory still shines. So, wherever you are, and whenever this moment finds you, breathe slowly, rest gently, and let the old light of Methuselah fade into the quiet behind your eyes. Sleep well, fellow traveller, here at home in a very old universe.